So my name is Raul Tempone, and today I was asked to give a slow and not so deep maybe introduction to uncertainty quantification and Monte Carlo methods. So thanks for having me today. This will be a mostly informal presentation, so I encourage you to stop me and ask questions whenever needed. All right? So don't feel guilty for doing that. It doesn't pay. All right, so this is a part of a course that I teach, and we have created together this material with a colleague of mine called Fabio Nobili, who is a professor at EPFL. All right? I do come from KAUST. That's the place in Saudi Arabia where I'm currently at. And the outline for today is just to give you some introduction and motivating examples, and then go through the standard Monte Carlo and hierarchical versions of it called multi-level and multi-index Monte Carlo methods. All right? I don't know exactly how much I will cover in this process, but I was expecting to, I think we have time until 5 to split it, or 4:30, yeah? Okay, to split it so it doesn't become too schwer, right? So let's see. I expect them to maybe take, until 1:50, the first part, and then we see how far we cover, right? Okay. So this is the place where I'm coming from. So just for you to know, because people ask where is KAUST and what happens. So let's go to introduction examples then. So we all know, and this is why we are here, that mathematical models and computer simulations are widely used in engineering and science applications. All of them, all these models have parameters that you need to fit, it could be material properties, it could be boundary conditions, initial conditions, that are not perfectly known, right? And you wonder, even if you have perfect accuracy in your numerical solvers, how much will be the impact of this lack of perfect knowledge in the prediction you want to make? That's a reasonable question, right? Particularly when you work with engineering, where you need to meet certain tolerances in the design and the predictions that you give. Okay, so the question is, in that case, well, the model that you're providing with the parameters that you have fit somewhere, will be able to meet these tolerances that you need actually for the engineering device to work. All right? So the purpose of this discussion then is to devise effective ways to include and treat uncertainty in a mathematical model, meaning that you're not only going to acknowledge this lack of perfect knowledge when you create the mathematical model, but you also try to take them into account when you do an efficient numerical simulation or numerical discretization, right? As you will see later on, it will not be a question of just, say, running your deterministic code many, many times, right, with different parameters to try to see an answer. This may not be, in many cases, the best numerical method to do, okay? And examples are everywhere because everything has uncertainty, right? So in all cases, essentially, you have certain parameters or certain geometries or things like that are not perfectly known, and it is really valid to ask yourself what will be the impact of that, again, lack of perfect knowledge in your computations. So I don't stop on this, I just include it for okay, so uncertainty can be treated in many ways. We can be very risk averse and say, okay, I want to work with intervals, say, and if my parameter is in this interval, I want to have an interval where my answer will be, okay? This would be almost sure type of answer, but the most widely used is a probabilistic approach, where you actually describe your inputs or your uncertainties somehow as distributions, essentially meaning that a parameter that is not known, right, is in a certain region, but we have, a PDF, somehow a probability density function that describes, that here in the center may be more likely to find this parameter, and as you go farther and farther away, it is less and less likely, still not impossible, right? Okay? So you can encode this soft type of information in these input distributions. Okay? So we are not going to then work with worst case scenario analysis, which is sort of this interval that I was discussing with you. Instead, we're going to focus on probabilistic descriptions of our uncertainties and then fit them into classical models, for instance, partial differential equations, and try to predict how this is going to impact the outcome of a particular computation. All right? So take a PDE essentially as a model to work with, and then once the parameters that are inputs to the PDE, call it a coefficient of thermal diffusivity, call it something else, a forcing for instance, are random, the solution itself becomes random. The solution U of the PDE, as we will see, right? I'm going to describe a few examples now, don't worry. So your question is, for example, what we would like to compute in that case, because I mean each outcome of the solution is itself random. So somehow what is there in reality is not going to match exactly the same realization that you're going to be working with in the computer. Instead, you're going to be trying to provide answers of the type, okay, the probability of the average of the solution in this subregion to be higher above a certain threshold that will create a failure in your design is this and that, for instance. Or the mean value of my solution in this region is that value, or the variance of that particular value in that subregion is this. Okay? So you will always be somehow given deterministic answers, because the probability of exceedance is just a number, it's not a random variable. The same with the mean, for instance. Right? So even though your model is stochastic, your answers are deterministic, and each realization per se doesn't make any meaning. Okay? Is that clear? So we are not after this U of omega x, if I can just repeat the point. Okay, so throughout the presentation also I will be concentrating mainly on real valued quantities, meaning that, again, like I was telling you as an example before, you have your solution U, right? This is a function that lives in a certain domain, and out of it you're going to compute a functional, a real valued quantity. So for instance, it could be the average of a flux in a certain surface, or the average value of the solution in a certain subdomain, right? But these quantities are real values. So if the solution was a random function, these quantities of interest, or outputs, if you wish, of the model are real valued, and therefore they are real valued random variables. Is that clear? Okay, I'm going to give examples again, but just to set where we are playing. And this will be called essentially Q of U, where Q is a function and U is a solution, right? Q itself is a deterministic function, it's not a random, but U being random creates Q of U, which is a random variable. Is that okay? So let's go to examples, because I mean sometimes when we speak in the air it becomes too abstract. So let's see linear elasticity with random elastic properties. This could be a cantilever beam essentially that is attached here on the left and is being pushed down on the right? And you have the classical linear elasticity equations, right? Written here in weak form. And this is your deterministic type of equation. Nothing has changed. The only difference here is that mu and lambda and possibly p, the weight, are not perfectly known. Okay? And you're going to describe maybe these parameters, input parameters now to your model, as random variables. Okay? So this is a single value p, this is a single value lambda, a single value mu. And what you may be interested in, for example, is to compute what happens with the displacement, average displacement of this phase on the right. Okay? And that's a real valued quantity. A function of lambda, mu, and p. The function is defined through the PDE, right? You give me lambda, you give me mu, you give me p, I solve the PDE, I give you the displacement on the other side, right? If lambda, mu, and p are random variables, then the output, just through the mapping of the PDE, becomes random itself, okay? Clear? So, in this case, naturally, in the way I described it, we have 5 parameters. If you think that this p could actually be 3-dimensional, acting on the face, right? So you have the Young modulus, right, and the nu, and the p1, p2, p3. So the whole point, and this is what we are going again to assume through the presentation, is that given this y vector there, I think we have a pointer here, but I don't know where it is now. Yeah, thank you. So given this y vector, which is the input to the model, right, you're going to create this output, and the mapping that takes you from y to u of y is deterministic, is the PDE, right? What makes this context stochastic is that y is going to be composed with a random variable, essentially, right? Because E, nu, P1, P2 will be random variables. And then the outcome through this function, the composition with this function, will be random, right? Okay? Is that clear? And just another thing. You give y, right, and q and u of y, it's a function, so it lives in a certain functional space. And what makes the thing real valued again is that we are going to apply a quantity of interest, a q functional, to this result, right? And then you get, again, into real values. Okay? So, in this case, we just have few parameters, namely 5, right? In other cases, you have many more. And this is what we're going to go through other examples. Okay? Seismic waves in random layer medium. Now you don't have like a static situation I just described, but you have time dependence as the waves propagate through this media, and you have certain layers with different materials, right? So each of these layers, right, have now density and the elasticity parameters to deal with, right? But also, in general, because you are not there digging everywhere, the position of these layers is not perfectly known, right? So you can imagine now how many parameters we need to describe this situation. We need to describe the geometry of all the layers and the properties inside of each layer. So if you thought that, this situation contained a few parameters, this other situation contains many more, right? So it is very easy in practical situations to go high dimensional in the inputs when you do uncertainty quantification, correct? Remember, all these positions and all these properties, in most cases, are known indirectly because we don't have the means to go and dig everywhere, right? So somehow you solve an inverse problem to get an approximate position for these layers and approximate properties for these materials inside, right? And still, having these things that are not perfectly known, you would like to do predictions, right? You would like to for example, measure something in the surface and know where, for example, an earthquake originated or something else. Correct? Okay. So you have many layers, and on each of these layers you have these parameters. So naturally, if you make the unrealistic assumption that the geometries of the layers are perfectly known, which is not true, you still may have a lot of parameters, because if we think of the previous example, you only have to multiply 3 essentially times the number of parameters, and this may grow very fast. And then you have the geometry parameters, right? So this could be easily high dimensional. So in this probabilistic context, you will assume that each of these parameters, or actually the joint vector here of parameters, has a density, a joint density that we call rho of y. This rho is not this rho. This is for the density. You see this slightly different. And this rho is from the probability density function. Okay? So don't get confused by that. Sorry for having to close the two of them. Just for simplification of the presentation, we sometimes make each of these layers that has different materials to have statistically independent parameters from the other layers, right? I mean, the properties of, say, clay are independent from the properties of, say, sand, right? So that's what it means really to have this multiplication here. And as I said, other parameters can be uncertain as well, like the positions, and this is very relevant, okay? So again, if you give me the whole vector y, I will return a solution that is now space and time dependent. And for this solution, we may apply functionals to know what is going on in particular places at particular times, right? We may be testing in this case how prone is a certain building to fall if you have a certain earthquake, right? In a certain place. So you will see the waves propagating through this place and see how they hit, how badly they hit in a certain region, right? And then you will try to compute the probability of this building falling or other related things. Yeah? Okay. So, if you have seen this before, these are the spaces that are natural for the solution of this solution, and nothing changes in this context. It's just that each of these occurrences of the solution depends on the input parameters y, nothing more. Okay? Yeah? Again, if you don't know something or you want to ask more, feel free. Otherwise, I will assume that you know everything, you understand everything, and my pace is going to increase, actually. Okay, another typical example is groundwater flow in random heterogeneous media. This is Darcy's law that essentially says that the flow of water in porous media relates to the pressure, the gradient of pressure, and this permeability coefficient K. So this is pretty much the heat equation, but in a different context, right? Same math. And you may have sources and sinks for the flow, and this is described by the divergence equation here. Now, what is uncertain in this context is this parameter K, okay, the permeability. And you would like again to make predictions because these are the equations that govern the water flow in aquifers. And for example, this is very relevant because you may have, for instance, a source of pollutant here on the surface related to industry or such things, and you would like to see how this goes into the aquifer and whether it contaminates water that later will be used for drinking purposes, for instance. Okay? So this is really relevant. What is the point that I'm making here with respect to the previous examples? That another way of describing variability in the properties with respect to space, right? If you assume here that K does not depend on, does depend on space, as opposed to the first example where you have, a beam and all the properties were the same, across the beam, is to use random fields, right? So in the second example, namely the seismic, we were using layers, right? So in the whole domain, the properties are not the same because on each layer, the properties are different. But within each layer, we assume them to be constant. In this context of groundwater flow, we may assume the permeability not to be constant, and there are no layers. So somehow the variability here is smoother, if you wish, okay? Continuous, if you wish, not like layers that introduce this continuity. So how do you do that, actually? Okay, so one way to do that is to assume that the permeability, actually the logarithm of the permeability, it's a Gaussian field, okay? And a Gaussian field, if you have seen it or Gaussian vector, if you wish, if you have seen it in other courses, is defined by its mean and its covariance, right? And for a vector, it's just a covariance matrix. But for a function, it's a covariance function. Essentially, if you give me two arbitrary points in space, there's a function that tells you what is the covariance between the value in this point and the value on that point, right? So they could become quickly independent, right, if the covariance decreases very fast, or you could have long correlations if this covariance does not decrease much, okay? So through the covariance, you can actually even control the regularity of the realizations of this field. For instance, you can control whether this is going to be almost surely CK, right? So this is very relevant. Not only how the correlation decays in space, but the roughness of each of the paths. So I'm not going to stop into that, but I just tell you that if you want to deal with the variability in space, Gaussian random fields is a very nice place to start. Okay, and the good thing is that again they are completely defined by the first two moments. You need the mean as a function of space and the covariance. And now the covariance, of course, is an object that if this is domain D, right, it takes D times D and then return real values, right? So it's much more difficult to deal with than the mean. Okay. Yes, please.
So for random fields, we generally assume that they are differentiable in space?
No, not necessarily. No. One of the most popular actually in the geoscience. Can I write here? Is there a pen or something like that? Or I can write here. Yes. One of the of the most popular models, I mean, I'm going to draw this in 1D, right? It's a stationary field, so essentially the covariance of the field, say k or log k, depending on the distance between 2 points, say y minus x, for instance. It's not just depending on the position. It may, if it is isotropic, it may depend on just this norm. Is sort of or proportional to exponential of minus, say, y minus x divided by L. And there's here, for example, sigma squared, which is the variance. Okay? So this is a correlation length, this L, which is positive. Right? And if you plot this as a function of this, you have a function that has a kink at 0. This is 0, 1 minus x. Everybody can see this, or it's just too low? So this function is not differentiable at 0. The differentiability at 0 for stationary random fields governs the realization's smoothness. This essentially has the same realization, the same roughness as the Brownian motion. Okay? So it's little less than C half. Okay? And this is still used in computations.
But the divergence of U may not be defined.
Well, U is related to the derivative of K, right? Somehow. So in this case, you can still make sense of the divergence. So the quantity that is not differentiable is K. So what this equation says is that K, U is related to K. So you get the C1/2, but you can still make sense of the divergence. You cannot still make sense of derivatives in all directions. That is different. But you can still make sense of conservation. Okay? Yeah, that's a good question, actually. But you can still make sense of yeah, I don't know if you can push it less. I don't think you can push it less, but that works. All right. Any other question? I can push this down. So, yeah. Through computations, though, when you have to compute with the field, this field, and you are going, for example, to use finite elements, if you just think of quadrature, which, you're all familiar with finite elements. So if you think that you have used a mesh there, and you have to use assembly, and this means quadratures inside of each of these subdomains. The number of subdomains is finite, right? The number of quadrature points per subdomain is finite. This means that you will only access K finitely many times, right? Because there are finitely many points where you're going to need to evaluate this K. And this will be a long vector, right? Long vector of random values. The log of those values will be Gaussian, and the covariance matrix associated with this long vector will be uniquely determined by the covariance function of the field. Okay, so you can always think that you're working with vectors if you wish. Okay? Yeah? Okay. This trick of the log is also important, and here's another point to make. It's very important to make sure that your computations are well posed. Okay, so in PDEs we know that, for instance, for this equation to make sense, you need coercivity and continuity, which means you need to have a control on the K coefficient so that it doesn't go above a certain value and doesn't go too close to 0 or actually crosses 0, right? So when you write your random model, you have to make sure that this stays like that. Okay, so to guarantee positivity, like I was telling you, one popular model is to take the log of K and work with actually the log of K, and we call this Y. All right, because again, by taking the exponential of Y, you're always going to get something that is not negative. If you do exactly what I told you before, which is to take Y as Gaussian, you have to be careful because Gaussians, are not bounded and can get to minus infinity, right? So in principle, as they get to minus infinity, K gets to 0, right? The good news is that the probability of that to happen is really very low. So the model still makes sense, okay? So for each realization, it will make sense, and then you can easily prove that you can compute any moments essentially, and they will be bounded, okay? But again, you have to be careful. Okay, so one way to deal with random fields, again, is to tell you what I did before, essentially is to work with the covariance function. If you have finitely many points to work with, you compute the covariance matrix associated to these points, you compute the mean associated to these points, and then you know how to generate any computations, right? The other is to try to do an expansion, and you can think of this as like a Fourier type of series, where you decompose the effect of randomness on one hand and space. Okay? So this is a sum now. You try to you approximate a random field that depends now on omega, which is a random input somehow, and space. You write it as the mean plus correction terms. And these correction terms here come through this possibly infinite number of random variables, collection of random variables, and these functions that depend on space. Okay, so again, it's like a separation of variables, right? It's like a Fourier series, although you're separating space from the random input. Yeah, this could be used also with space and time or with time, same type of thing. So yes, so in the case of Gaussian fields, you can work so that these variables here, y, are all Gaussian, normalized, and they're all independent. Okay? In general cases, you cannot do that, but for the Gaussian case that we were discussing, this is possible. Okay? Okay. So we are not going to go crazy with respect to the solutions. We will always assume that there's a unique solution with respect to the random input, and also that the solution is well posed. Essentially, if you perturb the vector y, the solution not only varies in a continuous way, it's possibly even much more in a smooth way with respect to y. Okay? I mean, in some of the most advanced methods, you end up trying to show that the solution is actually analytic on the input y to get the best rates. But this is not always possible. So, okay. But in practice, we never work with infinity, right? We truncate here by some way. So again, as I told you with the case of the quadrature points, you only work with finitely many random variables, right? So in the case of the finitely many quadrature points, we have a vector, say, of 1,000 points to evaluate, and essentially we reduce the computation to work with a vector of 1,000 random variables that were Gaussian. In this case, if you have, say, 5 terms in the expansion, right, you only have to work with 5 random variables, even if you have to work with, say, 1,000 points in the quadrature points. Right? Because you have decomposed it in this way, so you fix the number of random variables, you sum this up, and then you have the whole field defined for any point you want to work. All right? Yeah. So I just want to observe that, okay, you may have less random variables here, but you have a truncation in this case. In the other case that I told you about with this covariance, you don't have any truncation. Okay, so there are pluses and minuses in this representation. That's what I want to tell you a little bit more. Okay, so this is an example that is related with time continuous Markov chains. I think for the sake of time, I will jump over it. If you're interested, you can tell me later, but this is not related to PDEs, and I will concentrate on PDEs. Still, I will leave this on the slides, and these are going to be shared with you. So, and I'm here for some time, so you can ask me. Okay, so just another example of a PDE, uncertainty quantification in compressible aerodynamics. In this case, you want to see the performance of planes, for instance, varying the angle of attack of the flow, the velocity in terms of Mach numbers, density and temperature of the air, and then you would like to take into account, for instance, uncertainties in geometries that may come through ice attachments to to the plane. Okay? And this may affect the way it flies. And of course, you cannot know these shapes precisely. Okay, this is another type of example of random geometry, right? So again, you go through the Euler equations and you have this uncertainty in the shape now of the wing coming from these attachments, and you may have other things as well. Like I said, you don't perfectly know how the air is coming into the plane, and all these add up to a final computation that will entail, for instance, the computation of the drag and the lift coefficients of the flow with respect to a particular wing. Okay? Again, these are examples for motivating what is coming. I'm not yet teaching, if you understand what I mean. Okay, so now let's get to it. This is a part 2, Monte Carlo, multi-level, and so forth. This is a little bit of scary content. So, what is the Monte Carlo sampling? Well, again, I told you that we will be working with this structure of having a vector of inputs, y, and then having a solution that is u of y, right? And the solution u of y comes from the solution of a differential equation. It could be an ordered differential equation, could be a partial differential equation, or something else. All right? So this vector, we will assume, comes provided with a joint density function, probability density function. You may say, where is this coming from? It could come from the books, because I read about the parameters. It could come from the solution of an inverse problem, because I got data. I tried to solve an inverse problem. I recovered these parameters y1 up to yn with not perfect accuracy, and then I have this sort of densities to represent them, and through those I construct this row, okay? And this row is sort of the knowledge that I have in the parameters that go into the model. We are not discussing the physics here. We just assume that the physics are given, so the physics are the structure of the PDE, and we assume that this is perfect, okay? So there's no model uncertainty, just input uncertainty. Is that clear? Okay, and we assume that we are not after the solution itself, but a given quantity of interest applied to the solution. And for that, we assume that we have up to p moments where p is sufficiently large, be infinite. Okay? All right, so what is our goal? Like I said before, we can have many goals. We can have as a goal the computation of the probability of this Q being larger than a certain parameter that will entail failure, right? We could compute the variance or any other moment, but for the sake of illustration, I'm going to consider just the mean, the computation of the mean. Yes? Again, it's for the sake of illustration. So, let's go for the first method then. This is a classical Monte Carlo approach. So what do we do? Well, you remember the expectation is an integral. Okay. So the expected value of this Q of u of y, is it possible to see here? Or this is more than you? It's okay? This, right, it's an integral of Q of u y against the density y dy, right? And this is over the space of the parameter y. Yes? So, from numerical analysis, actually, you know that you can use a quadrature for this integral. Yes? So, for instance, if this is just a one-dimensional set, you can just use your favorite quadrature, and assuming that these two functions are smooth, right, you're going to approximate this by a sum over quadrature points, okay, that we call yi, say, times weights. Right? These are the weights of the quadrature. They add up to 1, and all these things. Okay? And you will get a certain accuracy in terms of the number of points that you use in this quadrature, and again related to the order of the quadrature you use. This is fine as long as you are in sort of low dimension. And what do I mean by small dimension? I mean that this gamma is actually included in a certain set, R to the D, and I'm referring to this D. Well, actually, if I have to be consistent with that, I think I use the number in capital, right, for the length of Y. So the problem is that the usual quadrature rules that you have in numerical analysis that are deterministic, as you raise the number of dimensions n, require an exponential work. Okay? So, and again, why is that? Is because if you're in 1D, say, and you use a certain number of points, and h is the distance between the points, the error is of the order h to the, say, p, where p is the order of the quadrature. You're familiar with this, right? Yes? Okay. And what is the work? Well, in 1D, the work is the number of points. So in 1D, essentially, if h is the separation between the points, the work, right, is essentially 1 over h. Right? That's the number of points. In dimension n, right, means that I have to take 1 over h points in this direction, 1 over h points in this direction, 1 over h points in this direction, and you have to multiply them. This is a tensor type of quadrature, right? So in dimension n, you have an n here. And even if you want to make this error of the size, say, epsilon, right, this means that h has to be epsilon to the 1 over p, the conclusion for the work as a function of the accuracy you want to reach is essentially epsilon to the minus n divided by p. Right? And this is pretty bad if n is a very large number, like for instance the case of the seismic example that I gave you before, right? Where you have plenty of layers, you may have even geometry related parameters. And easily you can get there to n equals 100. So even if you use a quadrature that is order 10, right? You will have 100 divided by 10, and this is growing like epsilon to the epsilon to the minus 10. That's right. Right? This is terrible news. So in high dimensions, you try to do something different, and this is where Monte Carlo comes in. Yes, please. If I get the time, yes. This is what I call the Multi-Index Stochastic Collocation? Yes, that's right. That's what I tried to reach to. But they told me langsam. So they told me to keep it. Yeah, so actually I stay here until August 14th. So if you want to have questions or discussions or anything, it's easy to find me. And I will provide the slides as well. So it's important that you get clear the first ideas and then we try to get there. Okay? Yes, please. The work is, okay, yes, you are familiar. Maybe I just express it in a different way. It is computational work. So if I have to do a quadrature, this means the approximation of an integral by a sum. The sum that I propose essentially is sum over values of the function that I want to integrate times weights. If I assume that the functional cost is a real costly part of the evaluation because it entails the solution of a PDE or something like that, naturally the cost is proportional to the number of points in the quadrature. Right? And that's what I said. I said, if you have a one-dimensional interval where the points are separated h, then the number of points in the interval is proportional to 1 over h. If you have now, instead of an interval, a hypercube, the number of points is 1 over h to the n, because it's 1 over h in this direction, 1 over h in this direction, 1 over h in this direction, and so forth. So the computational work... This is a small number. H is going to 0. If I want to get approximation, h is going to 0, right? This is my error, essentially. So h is a small number. Okay, so this is blowing up. And so is this. When the accuracy requirement goes to 0, the work to achieve it explodes. And the problem is that, it explodes exponentially fast in the number of dimensions of your input. That's what we call the curse of dimensionality. All right? And that's why one has to do something better than just a tensor type of approximation. Therefore, the question of the sparse grids. Yeah. Okay? All right. So if one doesn't want to do this, instead, one can try to do Monte Carlo. Okay? And what is Monte Carlo? Instead of writing this approximation in terms of quadrature points that are deterministic, we say, well, we sample the values of the yi's and we give them equal weight, essentially 1 over the number of samples. That's a sample average, sample mean average that is very much used in probability in statistics. And we know that as m goes to infinity, the right-hand side converges to the left-hand side. The good news is that, the rate, essentially the rate in terms of the number of samples, that will be the work in this context, is provided that the variance of the quantity we're computing is finite, independent of the length of the input. Okay? And we're going to see a little bit of that too. But this is what makes Monte Carlo robust and attractive for high-dimensional integration situations. Because it doesn't suffer from this effect that I was telling you before. All right? Yes, please.
What is omega in this case?
Well, omega essentially is just a probabilistic notation. We never know exactly what omega means, but it really means the outcome, right, of the random variable. So the actual value that the random variable will take. That's essentially what we mean. So y, once we compose it, is a function from omega into, say, r to the n capital, right? And given omega, you have the value of y. You can just think for your own sake that omega is just the outcome when we sample y. Okay? Y is in truth a function. Okay? It's a random variable. A random variable is a measurable function, right? From omega into r to the n. So if you want to keep it just simple, just think of outcomes. So essentially, I roll the dice, right? Take one value, roll again, another value, and what we are assuming here is that the values that we are taking are statistically independent and they are identically distributed. So all these sort of strange values that you see here, depending on omega m, they're just a collection of m capital random variables, all with the same distribution, namely they all have the same PDF that we say today, rho, and they are independent. Okay? So either you think of this as being outcomes, or you just think that these are m capital random variables, all of them with the same distribution, and all of them being identically distributed and independent. I just said identically distributed. Okay?
And so n would be much smaller than the dimension of your the parameter space.
Well, it depends, right? It depends. It depends on the accuracy you want to get. It depends on the value of n. I'm going to get you the rate of convergence, and then you can compare the two. But it will depend on the problem. In a very large dimensional case, it may be, like you say, that m will be much smaller than n. But this is not always the case. What you do expect to have with this method is to have less work than with this other method. This is what really counts. Okay? So I just can tell you a little bit more of what is coming. Here we get this dependence of the accuracy versus the work that you need to pay. Okay? In Monte Carlo, instead, we will have W Monte Carlo of epsilon to be essentially epsilon to the minus 2. If you disregard the cost of evaluation of each PDE, which actually I did here, so this is a fair comparison. So these two does not depend on n. Okay? And when this quotient actually becomes larger than 2, boom, this is more attractive. That's really what counts, not whether the n capital is less than m. All right? You care about computational work. For a given accuracy, you will get to use the method that gives you the less work. That's what really counts. Well, we will see that it can be improved. But first I have to tell you the properties. Okay? So, and I have not even scratched the surface of I'm just describing the method. First, I describe the method, then I tell you the analysis of it. But I just told you essentially what you expect. You expect a 2 there, and the 2 can be much better than this n divided by p. Okay? So this is Monte Carlo in this context. Observe that this U implies the solution of a PDE. So each time you go and evaluate one of these terms, you have to solve a PDE. Okay? So maybe this is a comment on what you just said. There are pros and cons in this method. One is the reusability of deterministic legacy codes, because the only thing you need to do is to have an old code and being able to pass the random samples of y and then get the answer and then average. So this doesn't mean any recoding of your favorite PDE solver, for instance. Very simple. Okay? Can be easy parallelized because you just generate these y's, then pass to different processors the solution of the different PDEs, and then each of them will give you back the value, then you average, it's gone. Okay? So it's what is called embarrassingly parallelizable. The bad news, well, or the good news, if you see it in this perspective, is that the rate in terms of the number of samples is essentially independent of the dimension, is m to the minus 1/2, which is the same thing that to say epsilon to the minus 2 here. Okay? And that doesn't depend on the regularity of u with respect to y. It just depends on the variance of this quantity being finite. The cons, essentially, is a slow convergence. In principle, you would expect some method to converge with faster rate than the square root of the number of samples. But if you see it in this context where classical full tensor type of methods give you epsilon to the minus n divided by p, well, maybe it's not that bad. As we will see later, hopefully, if we are able to exploit possible available regularity of u with respect to y, we can do better. But okay, let's see how far we get. Okay, let me tell you about the error then, and then we can stop. So let's see. This, if you remember, was the quantity we wanted to approximate. This, on the right-hand side, is the quantity we actually compute using Monte Carlo. And as you see, there are two sources of errors here. One is because instead of computing an expectation, I took a sample average. Second is because instead of having the exact solution of the PDE, I used a finite element or finite difference or whatever you want to call it, approximation of it. And this is denoted by this small mesh parameter h. And we all assume that as h goes to 0, UH converges to U in the proper norm, and the work, the computational work to evaluate UH goes to infinity. Otherwise, we will always take h equal to 0 and don't bother about it, right? So to understand how the error appears here, we say the following. Okay, we try to split the contribution from h and m. We sum and subtract the exact expectation of the wrong quantity, which is the expected value of q of UH, and then in this part here, we only depend on h. And this is essentially the average of the classical discretization error in numerical analysis. Okay, so you have an order 2 finite element, right? The error here, you expect it to be like constant times h squared. The constant really depends on y, because the coefficients of the PDE depend on y, correct? And then essentially you get an average of that constant times h squared. That's not super exciting, but it is what it is. On this side, though, you have an expected value and an approximation of it by a sample average of IID, identically distributed independent outcomes. You see that here and here, you have UH. Therefore, if you take the mean of these part, you get exactly this quantity. So this is an unbiased random variable. The mean of this term here is 0, always. Okay? So there's only statistical error here. You just want to check essentially the probability of this mean 0 random variable to go beyond a certain value. That's what you really care. Okay? And that, in this Monte Carlo method, is usually understood through the variance. Okay? And this is coming essentially through the central limit theorem. So, yeah. Okay? There's one last thing to say here. I say that this depends on H, and this mostly depends on M. Why mostly? Because there's still a dependence on UH here. What we assume essentially, and this is reasonable to assume, is that this H doesn't have a dramatic influence on this quantity because the variance of Q of UH is bounded uniformly with respect to H. Okay. We'll discuss a little bit more about that. So the real dependence on the second term is on M, not on H. Okay, so let's go a little bit more. So let's see the Monte Carlo error analysis. I want to discuss two things then, the discretization error and the statistical error. Let's see the discretization error, and it will behave like I told you before. So about the quantity of interest that we are computing, remember, we have a function, we apply the quantity of interest, we get a real value. It could be an average of the subdomain, or a flux, or things like that, but it's a real value. All right? Now we assume that it's globally Lipschitz, essentially that Q of U minus Q of V is less than a given constant that depends on Q, that's U minus V in the proper norm. And then again, we assume that we have finite moments for this constant. Remember, I don't emphasize it too much, but this constant here depends on the functional. Okay? And now we make an assumption that the solution of the PDE is such that we have an approximation between the true solution for a given y and the finite element, say, solution for the same y, like this. And this is the usual classical numerical analysis error bound for a given alpha degree order method. And here the constant depends on y, obviously, because the coefficients of the PDE depend on y. Okay? Is that clear? So now we know how to essentially estimate the mean error, essentially the difference between Q of UY and Q of UH. We just use first the fact that we can bound this difference by the CQ times the norm. Then we use the norm bounded by this, right? And then once we pull out the H to the alpha, this is an integral and it's a given value, like I told you before. So essentially what we are doing is to average the classical deterministic error. It's nothing more. I told you before. I repeat it here. Is that clear? Okay, and that's the result. Okay, so this truly depends on H, and you expect the same order as with your deterministic code, unless there's a strange singularity that appears for particular values of y. And we are not assuming that, so nothing changes there. Is that clear? Okay. Okay, so you may say, okay, how difficult is to verify these steps? Well, let's take again this classical example where A now is written in terms of a finite many number of random variables here, yi, and we assume that actually we have coercivity, namely that there are no values of yi that will make this to go below a given value delta times a bar, right? And then you have the coercivity and the continuity for all values of x and for all values of y. And from here you get the classical control on the UI for all the y's. You see that this doesn't depend on y anymore. This is the classical bound of H1 norm of the solution. And you also have a control on the H2 norm. And this is important because the H2 norm is actually what gives the convergence rate of the finite element, at least if you use piecewise linear. Okay? And again, this doesn't depend on y anymore also. So if you go through the finite element analysis here, you get as a conclusion that the error, right, in any p norm actually, not only in L2 but also in H1 is bounded by this quantity. Okay, you have an H here, so this is classical, right? You have one order less in H1 than in L2. Okay, I'm just trying to tell you that there's nothing strange to add here. All that you know already in the deterministic case is true and it appears as averaged in this context. What really comes different is through the other part, the statistical part. Okay? Okay, so from here you can also conclude that all the moments of Q of U and therefore Q of UH are bounded. Yeah, so you have this thing here. Now let's go to the statistical part and then we take the break. So as I told you before, the difference between these two quantities here is a random variable that is unbiased for any value of m. Namely, the mean value of this error is always 0. Right? And why do you conclude that? Well, you take expected value here. All of these are identically distributed, so they give the same mean value, namely this, and you have m terms divided by m, you get the same value as here. Okay? Now, if you compute the variance on this quantity, right, the variance of this quantity, again, each of the terms here is identically distributed. They are all independent because by construction, each of these samples was independent of the rest. So when you have a sum of independent random variables, the variance of the sum is the sum of the variances, right? Yeah? Okay. And also, you have a 1 over m here acting quadratically, so essentially you have m times the variance of these terms and divided by m squared, because I mean the variance again is a quadratic form on the 1 over m term. So you get, as a result, the variance of this quantity here is 1 over m times the variance of this. And we said that the variance of this is uniformly bounded with respect to UH. Why? Essentially because UH is convergent to U and U has finite variance. That's really what happens here, and is what actually I took the effort to write here for you. So you really get convinced that this is not really dependent on H as a size, right? Why? Because again, you sum and subtract the true U here, and you get something that is going to 0 as H tends to 0, therefore is bounded, and this quantity doesn't depend on H. So the whole thing here is bounded uniformly with respect to H. Is that clear? Okay, so you expect this variance to be bounded by a given value, say 1. That's important. So once you understand that, you can say, okay, you can analyze this type of convergence, right? The probability of the statistical error, right, being larger than epsilon, and this you can bound just by the Markov inequality as the variance of this quantity divided by epsilon squared. But the variance of this statistical error was essentially a constant divided by m. That's essentially what I just showed you. And as m goes to infinity, for epsilon fixed, this goes to 0. Okay? So the statistical error really converges to 0 as m goes to infinity, for example, in this sense. There are other senses of looking into the error as well. For instance, you may want to compute just the expected value of the square of the statistical error. That would be L2 type of convergence. And you can show again that obviously from the variance computation that I did, that converges like 1 over m. Is this clear, or you have questions for me? Again, if there are no questions, I understand that you understand. Okay? Sie verstehen. Yeah. So, there is mathematical theory that actually guarantees that this convergence actually happens. I actually, for references, include the statements of the weak law of large numbers and also other type of convergence that you may have seen in the past, but you want to refresh for this lecture. Okay, so we have L2 convergence, like I said before. We show directly that this was 1 over m. I just discussed this other convergence with probability. I did not discuss, and I will just mention the law, the iterated log law with respect to this one. And this is related essentially with the central limit theorem, which is the most important result to deal with when you try to numerically understand the convergence rate of Monte Carlo. Okay? But I will come to that. Don't worry. Don't get stressed by this. It's just for reference. Okay. So again, strong law of large numbers. I don't need to iterate on that. Rate of homogeneous convergence. This is not relevant for what I'm going to do. This is an example that motivates essentially what is going to happen. So this is something where I would like to stop, and we take, say, 10 minutes is okay. So we see each other at 2:15 here again, and we continue with the convergence rate of Monte Carlo in terms of the samples, and then I will add also the computational work from the PDE solve. Thank you. Thank you. I was trying to motivate for you the rate of convergence of Monte Carlo with respect to M, which is the number of samples. Okay? By the way, has anybody not seen Monte Carlo before? Is this the first time? Okay, good, good. Then it's good. What I'm going to say is good. For those, for the others, this is refreshing material, which is also good. Okay, so what are we going to do? First, I'm going to discuss an example with actual computations that will motivate what to expect, and then we will see why it really holds. So let's begin with the computation of an integral, like we were doing here in terms of the random variables. But this is just a deterministic integral. So we are going to take the integral of a function f that is real valued over the hypercube 0, 1 to the d. D in this case is playing this n capital number of random variables as before. Okay? So, of course, here you have the function 1 to the d, and this 1 to the d can be understood as a probability density function of a random variable that is uniformly distributed with components that are independent in the interval 0, 1. Right? So this is nothing strange, and therefore this is just equal to this expected value. So you see, we wrote a deterministic integral as an expected value, and then we apply to that Monte Carlo. And the approximation here is a random variable, even though the quantity we are computing is a deterministic number. Okay? So for each fixed m, this number is a random variable that we denote as im, whereas the true value is just I. All right? Yes? So we are going to sample uniformly these values over the hypercube 0, 1 to the d. So each of these outcomes will be a random vector whose components are in the interval 0, 1 and who has d components. Yes? You can just take this function as an example, because in this function you can just know exactly the answer. So you can check exactly the exact error, right? And this is just a MATLAB, a few lines of MATLAB to show you what is coming. So what do we do here? We compute the computational error, and we show this computational error here in absolute value sense, right? So we take the difference between the true value and the approximate one provided by Monte Carlo. We take the absolute value of that difference, and this is what we are showing here as a function of the number of samples we add in that average. Okay, so at the beginning the error is large, and then it behaves quite erratically. Sometimes can give very low values, but you cannot predict essentially when this happens. But you see sort of an envelope here, and this envelope is somehow parallel to this red line. And this red line essentially it's m to the minus 1/2. This is a single realization of the algorithm, so you may say it's not so parallel to this, right? But you see, each time you run this algorithm, the blue curve will change. Okay? So what really makes sense here is to run this algorithm many, many times and see really what happens. So what you're going to do now is to run this algorithm starting with, say, 10 realizations and going up to, say, 1,000,000, and see how the error for all those runs behave. And then you see this. And then obviously the envelope that I was talking about becomes more evident. All right? But now, okay, now that you really expect this convergence of m to the minus 1/2, you try to understand what is the constant in front of it, right? Because as a numerical analyst, essentially, you'd like to predict the error to see how to improve your approximation. So you may know that the error is decreasing like m to the minus 1/2, but you need to understand the constant. And if you see from the plots that I gave you, extrapolation will not really help you much because the curve is very erratic, right? And changes for each generalization you make. So this is actually, by the way, 20 times you run the whole averages, set of averages from 10 to the 0 to 10 to the 5 or 10 to the 6 actually. Okay, is that clear? Okay, and this is the plot essentially. So this is the main result that you need to understand how the Monte Carlo error behaves. So what you do is the following. You take the sample mean, right? This was the average of m random variables. You subtract the mean out of this average, multiply times the square root of m, that difference, and divide by sigma. And this now quantity, which is a random variable still, that depends on m, still, as m goes to infinity, converges weakly to, or in distribution, to a given random variable here. And the given random variable, surprisingly, has a fixed distribution that does not depend on the input distribution of the yj's. Okay? That's interesting, because you're averaging random variables of any kind, essentially. You're just assuming that they have a finite variance, but nothing else, essentially. Okay? So what do we mean by this convergence with convergence of the distribution? Essentially, it means that if you take expected values of a function that is sufficiently nice, essentially it's continuous and bounded, of this random variable, right? And you take expected values of those, essentially you see this is essentially this. This, which is now a sequence of real deterministic values, as m goes to infinity, converges to this real value, right? And this happens for any j. The rate of convergence may depend on j, of course, but this happens for any j. And this distribution is fixed and does not vary with respect to the input distribution of the y's. That distribution is normal with mean 0 and variance 1. Okay? So, any questions? You have seen this theorem before, right? In some form. Or? Yes. Okay. So this is actually the main result. And why is that so? Well, this y bar minus the mu is the actual error in Monte Carlo, right? In Monte Carlo, we approximate the true mean by its sample average. So this quantity here is the true error we want to understand. And what this is morally telling you is that the true error essentially behaves like what? Like a random variable whose distribution does not depend on m, divided by square root of m and multiplied times sigma. Okay? And if you then want to control this or have some idea of this error, you just have to understand what is the probability of this null to exceed a certain interval, right? Because that will control the error. You see what I mean? So if you have a bound on this null, well, the bound for this error essentially will be of the kind bound of the null multiplied times sigma divided by the square root of m. Okay? Yes or no? Yeah? Okay. You can see this numerically, and I put some examples here just to understand how these sort of distributions start appearing. And this is a rescaled experimental CDF for the Monte Carlo error versus the limit distribution. And this is using essentially 10 independent experiments and then 1,000 experiments. The 1,000 experiments are really close to the to the true one. Okay. You see that it's much closer than before. Okay, so I was telling you how to understand the error. I told you that the error is this, right? You can write it like that. By the central limit theorem, we are showing this. And essentially, this is telling us that the probability of having this less than C0 is essentially approximated as m becomes very large, like the probability of a normal 0, 1 random variable to be less than DC0. And this can be understood very well, it's tabulated, and you know everything about it. Okay? So essentially, in probability here, you're bounding the Monte Carlo error by C0 times sigma divided by square root of m. Okay? Any questions? No? Okay. So, one thing to emphasize extra, in a Monte Carlo computation, you're given two numbers. I mean, as opposed to the usual type of deterministic computation. In the usual type of deterministic computation, you have something to compute, and the user comes and says, I want accuracy 2%. That's it. Okay? Here, the user would say, I want accuracy 2% with a confidence level 95%, for example. Which means that 95% of the time, Monte Carlo should give you the accuracy of 2% that you wanted, but only 95% of the time. If you want, say, 99% of the time to hold, then you will have to increase this C0, right? And essentially, control this probability that is the confidence related to the confidence level, and this will give you a bound on the error that is slightly larger. Okay, so in Monte Carlo, there are two numbers to give as a user: the accuracy you want to get and the confidence in that computation. That doesn't happen much in the deterministic world, right? Okay, good. Okay, there's another point to make here. If you're actually using these for practical purposes, you're going to need the standard deviation related to the random variable you were computing. And remember, the whole point was to compute the mean, so it's a little bit absurd to believe that you know the exact standard deviation. So instead of using the exact standard deviation, you may use a sample average based of it, okay? A sample standard deviation of it, right? So that's another bit of a crime, right? Because there are two crimes here. One is that m is not infinity, so I'm really not entitled to use the central limit theorem. And two, if I'm using the central limit theorem, I should put the right sigma here, but I don't have it, so I'm going to put an estimate. So there are two crimes there. It's good to be aware of those. Okay, so now if we actually do use the central limit theorem bound with C0 equals 3, which is a relatively large confidence level, you get this, and you see that the bound is really decent. Okay? Now, we do this again for 20 runs of the Monte Carlo sampling with C0 equals 3, and using this approximate bound of sigma hat, which is the sample standard deviation divided by square root of m. And what do you see? Well, you see that some of these things go above, right? Particularly for small values of m. Why would you expect that? Yes? Yes. Okay. There are two crimes that actually become less and less as m goes to infinity. One is that we are not using the correct sigma, and the other is the central limit theorem is a limit. So it doesn't hold for small values of m, not nearly close. Okay? Thank you. Okay, this is a small discussion of the curse of dimensionality that I already made at the beginning, so there's no need to go through that. You can discuss it again. Variance n is an improvement on the central limit theorem, and essentially gives you a rate of convergence of the central limit theorem. Essentially says the following, that if you scale again, like I was telling you, the Monte Carlo error, multiplying the square root of n divided by sigma, this Zm is a random variable which is going to essentially converge as n goes to infinity to a normal 0, 1 random variable. And you can see it in this theorem from this point of view, that the cumulative distribution function of the normal minus the cumulative distribution function of this Zm, they differ in a quantity that goes to 0 as m goes to infinity, and this is not a limit. This is not a limit anymore. It's a bound. Okay? But as always in numerical analysis, if one thing is to show convergence, and the other thing is to show convergence rates. To show convergence, you need less assumptions than to show a convergence rate. Right? Because the convergence rate is a speed on how you attain a limit. Whereas in the other, you just show a limit and there could be essentially no speed to get to that limit. In the central limit theorem, we assumed only that we have two moments bounded, the mean and the variance. In this one, we need also the kurtosis, the third moment essentially, to be bounded. And the kurtosis appears here in the constant. So if you really want to have like this type of uniform constraint, uniform bound, you need to have this lambda bounded. Of course, these three here and these three here, you see that this is x, the same x here, are not a coincidence, essentially. If you have more moments bounded, you can get faster rates here, but this constant actually becomes horrible to track. The square root of m doesn't depend on that power, but the dependence with respect to the tails, they do. Why do you expect this error actually to go to 0 for a fixed m when x goes to infinity? Any idea? This is the kurtosis, right? This is the third moment. Essentially, it's related with the third moment. Yeah? So what I said is that if you have a higher moment, finite, you can pull out another rate here that is faster with respect to the tail. Now I'm asking, for a fixed m, this error goes to 0 as x goes to infinity. Does it make sense or not? Yes? Okay. So for everyone, this makes obvious sense or not? No, I mean, it makes sense from the formula, but without looking at the formula. Would you guess that? No? Okay. You remember, the CDF is a monotone function. That goes to 1 as x goes to infinity, and to 0 when x goes to minus infinity. And this holds for any CDF. So any other actually will do like this, for example. So you expect the largest error to be in this region, right? But as x goes to infinity, they both converge to 0, and they both converge to 1. So the difference converges to 0. How fast does this go to 0? Well, it relates to the convergence of the tails. And this is why the moments matter in this x convergence. Intuitively, this is very obvious, but I just wanted to check if you saw it. Okay. Any questions? Yeah? So we have a rate of convergence in the Monte Carlo estimate, and we can use this to improve a little bit the bounds on the central limit theorem. So how does this improve it? Well, it removes the necessity to take m to infinity, but it still leaves here two moments, sigma and lambda, which are not known. And you're going to try to approximate them based on sample estimates. Okay, so we remove essentially one crime because now we have a true inequality, but we need another moment. Okay, so we made an assumption, and we need to do sample estimates on the lambda and the sigma, which again, they need higher moments for things to work. Okay? If you assume many moments more, actually, than just the third, then you may get actually to an exponential convergence with respect to the tails. And this is an export expansion, but it's no longer, you see that this is no longer an inequality. There's a little O of 1 over square root of m here. So this has a much nicer behavior than the 1 over x to the cube that I had before, because it behaves exponentially, essentially. But you see, if you compare here, you see the improvement is in this part with respect to this part. The 1 over square root of m is still there. The lambda cube is still there. Okay? And you can actually see this advantage when you have random variables that are bounded or have very thin tails. And in this case, I took the sum of Bernoulli's, which is a binomial, and did the computation and see actually that the variance n bound will be something like this, that essentially is decreasing algebraically with respect to this x, but the true error actually is behaving much more like the Edgeworth expansion, which is converging exponentially with respect to these x values. Okay, so you actually can observe this type of Edgeworth expansion in particular cases. Okay, so that's what I say essentially, that the last figure actually shows you a behavior like this, which is much closer to the Edgeworth expansion than this one, which is the variance n. But you need more assumptions. You need just exponential moments to be bounded, which is much more than just, you know, algebraic moments. This is a small digression now on the PDE example that I had before, right, where this A was random. Essentially, it was uniformly bounded in terms of this finite sum of n terms. And in here, you can show, actually, as I told you before, that you have any moments, in particular the third, to be finite. And then you can use the variance n to bound the probability of this error to be larger than this bound. Okay? So you can actually use this in practice in the context of PDEs as well, if you verify the finiteness of the variance A and the third moment. Okay, so what's the next point that I want to make? I want to make the same discussion that I made today, where I assumed that each of the samples was a PDE that cost essentially O1, but now I will let the cost of the PDE depend on H, which is a natural thing to do, right? And optimize both M, the number of samples, and H, the mesh size, to achieve a certain accuracy restriction, right, with minimal work. And this will give us how much we have to pay for Monte Carlo in terms of the input parameters. And then we will be able to compare this with other methods. That's the whole trip that we are making, right? Okay, so remember there were two errors, right? The statistical error and the discretization error. One behaves like this, right? Like the usual deterministic finite element one. And this behaves like that. This is a constant that is bounded, so it's 1 square root of n. So the total error is actually the sum of both, and it's bounded above by this. So we are going to impose that this essentially is less than a certain accuracy, and we are going to try to minimize the total work. And what is the total computational work? Is the number of times I need to solve my PDEs times the expected cost of solving each PDE. What is the expected cost of solving the PDE? At least in the linear elliptic case that I gave you, well, let's remember, we are in dimension D, right? D could be 3. We're using a mesh size of size H. So essentially have 1 over H points, 1 over H points, 1 over H points, essentially 1 over H to the cube, right? That's 1 over H to the D that is here. 1 over H to the D is the number of, unknowns in your solution. But you have to solve a linear system. And the linear system, you solve it by just either Gaussian elimination, brute force, that will give you a constant cube here, gamma cube, or by an optimal method, if you're lucky to have one, and that will give gamma equals 1, right? Yes? Okay, so it is natural then to assume this model for the cost with respect to H. This is the cost with respect to each PDE solve. Is that clear? Yeah, okay. So number of samples times cost per sample. And the constraint is, statistical error plus deterministic error being less than something. You go and solve that, okay? Just use Lagrange relaxation. I just write it for completeness. And then you realize that the work of Monte Carlo in terms of an accuracy prescription that is of order tall, say, so my user wants to get accuracy tall, is essentially tall to the minus 2 plus d gamma divided by alpha. And in terms of, you have sum of exponents here, this means product. So this is tall to the minus 2 times tall to the minus d gamma divided by alpha. Told to the minus 2 is the number of samples that we needed essentially in Monte Carlo, the one that I told you today. Told to the minus d gamma divided by alpha is the cost per sample so that the bias in that sample, the deterministic discretization error, is below toll. Remember, what was the bias? The bias was essentially h to the alpha. Right? Yes?
Did you already say this is all assuming like a first order accuracy for H?
No, because you have an alpha here.
Okay, so yeah, got it.
So, and this alpha shows here. So as the order increases, the cost will decrease, of course. Okay? And as the dimension goes up, or the solver becomes worse and worse, this goes up. So it's a fight between the dimension in the spatial, in the spatial direction, the quality of your solver versus the order of your finite element, so to speak. Okay? So, but I was saying, essentially, this term here, this exponent here, comes from the fact that you're trying to make h to the alpha less than toll. This gives you h essentially to be of the order of toll to the 1 over alpha. And when you go and substitute it here, which was h to the minus d gamma, because it's the cost, right? This gives you toll to the minus d gamma divided by alpha. That's exactly this. Okay? So how do you interpret this? This is a work of the number of samples that are needed to make the statistical error less than toll times the cost of making a given any given sample to have a bias error less than toll. Okay? So you pay more than just toll to the minus 2 because each sample becomes more and more expensive as you make the accuracy constraint more and more stringent. Yes?
How did we lose the coefficients C1 and C2?
The C1 and C2 are just hidden in the proportionality constant here. Okay? They're just constant. What we really make an emphasis here on is the exponent. Okay? So really what we are trying to get here is the order with respect to the accuracy input. Those here will not depend on toll. That's the whole point. Okay? Good question. Okay, you can also do central limit theorem for random vectors. I included here for completeness, but I'm not going to discuss quantities of interest that are real that are vector valued. You can have more readings on Monte Carlo, and you can ask the following interesting question now. Given a problem, right? And now I'm not discussing PDEs anymore. I'm just taking one step back. Or you want to sample a random variable, right? We have this issue of the crimes that we made, right? And we have to be aware of that. We assume that we knew exactly the statistical, variance, sigma square, which is not true. And we also assume that either we go through the central limit theorem and we take a limit for being true when it's not, or we go through the variance n and then the limit assumption is gone, but we have an assumption on the lambda, which is the third moment, and possibly higher. Okay? So this is what I actually summarized here. Essentially, if you want to have an algorithm that, given a statistical tolerance and a confidence level, gives you the number of samples you have to take, this algorithm will give you a random number m because you are not going to sample perfectly the sigma, right? So, and in that crime, essentially, let's see here. Here's the probability of your true error being less than the prescribed tolerance. Okay, that's what you would like to have of the order, say, 1 minus delta. Okay, where delta is your prescribed confidence level. Remember, we said the user gives two numbers. One is the accuracy toll, and the other is the confidence level delta, or 1 minus delta, depending on how you want to call it. Okay, here, just by introducing this scaling that is multiplying by the square root of m and so forth, you can write this as this. Nothing has changed, right? Just notation from here to here. And now you say, well, I'm going to approximate this probability by this probability, where this z now doesn't depend on m and is the one coming out of the central limit theorem. That's what we call the error from the central limit theorem. It's what the remainder that variance n tries to bound. And the last crime that we make is that instead of putting this true standard deviation, we put s, which is the sample standard deviation. So there are two crimes in this approximation that we usually make. Okay, and of course one can try to just do like this, right, with respect to this crime, and use it use just this coming out of the central limit theorem as a stopping rule, saying if I estimate this error indicator, if you wish, and this is less than tall, I stop, and this is my M. I'm going to give the answer. This works in some cases, but for kind of heavy-tailed distributions, this fails badly. And I'm not going to stop too much into this because it's not coming into topic. But one can have works on making this rule, this to find M more reliable. So I give a couple of references in that direction. Okay. So this is just one example of that. Essentially, you have a probability density function that decays like x to the minus 4 almost. Okay, so it has finite moments bounded, and then the red part is where the usual algorithm will fail, which essentially says tolerances that are not too small, but confidence levels that are stringent. And that's usually common in practice, right? You have an engineering computation, it will be required to be accurate on the level of 1%, for instance, but or say 5%, but it will require, say, 10 to the minus 3 for confidence. Okay, so you have to be aware of these things. So there's a way to fix this without increasing too much the cost, but I'm not going to stop that again for the sake of time. Okay, so what do I want to tell you now? This relates to variance reduction. Okay, so what is the motivation of all this discussion? Essentially, the Monte Carlo error, again in probability and thinking on the central limit theorem, behaves like, again, C0, which is coming from the confidence level, variance divided by M. Okay, so M is here my computational effort. And I want to somehow reduce my computational effort while keeping the same confidence. So this C0 cannot be touched. The only thing that I have to try to touch is this variance of Y. But the variance of Y is something that is just defined by the problem that I'm solving. Right? So it's kind of weird. I don't know the expected value of Y. I'm trying to compute it. But now I'm going to try to make a transformation on the problem so that the expected value of Y is unchanged, because I don't want to touch the quantity that I want to compute, but the variance of Y is reduced. It looks like crazy, right? Okay. Okay, so we're going to create a new random variable Z such that it has the same expected value of Y, and hopefully its variance is much smaller. And then the number of samples M will be much smaller than in the original problem. That's what the name variance reduction comes from, essentially. Okay? Okay, so if we do it in this context, right, the rate with respect to the number of samples will not be changed, only the constant, remember, because we're going to be changing this value, right, but the slope with respect to M, that will not change. Okay, so we're going to just shift this convergence by a multiplicative factor. That's it. Okay? Yes, please.
Practice, does anyone ever only want the expected value because you lose the other statistics here, right?
Say it again.
You're no longer predicting the variance of the expected, of the random variable rate. So you're losing everything except for the expected value.
Yes, but you can reconstruct the variance as well in terms of moments. So you could do a computation with the variance as well. So, but that will bring me into computing sort of vector values, which I was trying to avoid. But you can do computations with vector values as well. And you can even do, if you want to be more extreme, you can compute with Monte Carlo and other versions of it, the cumulative distribution function of a random variable, which defines automatically all moments. Okay? So that's really not an impediment. Okay. Again, it's a good question. Unfortunately, I'm not describing the answer. So, okay. So of course, this will not the choice of Z will not come out of the blue, right? You need to know something about the problem in order to construct a suitable Z. Okay, so, all right, so let's do something really silly, and you will see. Why was the input random variable? We assume now that we have an auxiliary random variable called X, which is correlated to Y. It could be positively or negatively correlated to Y, but for which we know exactly the expected value. Okay, so we make a strong assumption here. We can sample together X and Y now. So we are sampling a pair, not just Y, but a pair, X comma Y, so that X is not independent of Y, is correlated to Y, and such that we know exactly the expected value of X. Is that clear? Okay, now, of course, the expected value of Z, that depends on this beta parameter here, will still be the expected value of Y, because, the expected value of the second part is 0. So that's trivial, right? You're just summing 0. But that modifies the variance, because the variance is a quadratic form in the beta. So if you go and compute the variance as a function of beta, is, something that has negative, let's see, has a positive concavity with respect to beta and can be minimized in terms of beta. Even if this covariance is negative or positive, really the thing that determines whether this has a minimum is this term. You minimize, you get the optimal beta star to be this value, right? And now you see that it's important that the covariance is not 0. And when you go and substitute the optimal beta star in the formula for the variance, you see that the variance of the new random variable, beta of Z of beta, the variance of Z of the beta optimized is the original variance times a factor that is strictly less than 1. Okay, so you have effectively reduced the variance, provided that the covariance between these two random variables is not 0. And they say, yay, I reduced the variance. But is that all, actually? Not really. Why? Because we started sampling one random variable, Y, and now we are sampling 2. So you're sampling a pair when before you were sampling, say, a single random variable. So if X essentially cost the same as Y, that would be double the cost per sample. So to beat the previous sampling method, you will have to reduce beyond half the number of samples, right? Because otherwise it doesn't pay. So even though you have reduced the number of samples to half of what it was before, if each of them cost, say, half or more, you're not winning anything. Okay, so it's just number of samples times the cost per sample. Remember, this is the right way of thinking. Okay, so how can we go beyond that? Well, let's discuss this a little bit more. So before we do any tricks of variance reduction, we were using Monte Carlo, right? And we knew that the number of samples that were needed to make the statistical error less than tall was essentially tall to the -2 times the variance of Y. Okay? And the cost of this Y essentially was assumed unitary. So from here to here, you don't see any change because I'm just multiplying times 1. Okay? Now we make the assumption that for this pair, the cost in terms of work with respect to just sampling one random variable of Y is 1 plus theta. Right? Where theta is hopefully a number that is less than 1. Okay? Yes? Now, if we use Monte Carlo and control variance, remember, I'm sampling each pair here. Now, the number of samples is this times the new variance, which hopefully is much smaller than this old variance. And the number of, the computational work is the number of samples, the new number of samples, times 1 plus theta. Why? Because I'm sampling a pair, and here I was computing just a single random variable. Okay? So, I remember what this was, and this essentially was this 1 minus something else times the variance of Y. So, this variance of Y times this factor are the same here, okay? And therefore, there will be a fight between 1 plus theta and 1 minus something coming out of this term. And this is essentially what you see here. This control variance for variance reduction will win, essentially with respect to plain Monte Carlo, as long as this product is less than 1, right? So if x costs too much, this theta becomes large, and then this may not be able to cope with it. Is that clear? So if theta costs almost nothing, this is 1, right? And you just need a slight correlation between x and y to make this work. And you see that there's always a square here, so it doesn't matter whether this is positively or negatively correlated. As it is, so you just need morally something that is somewhat correlated to y and costs little in terms of, you know, the sample of each of the y samples. Yeah? So now you know. So essentially, this is inequality, right? This is an inequality that x and y have to satisfy in terms of correlation with respect to the cost of the added cost of sampling x and not just y. All right?
Sorry.
Yes, please.
So assume that we know the covariance of x and y exactly.
Well, I said this before, but I ran too quickly over it. In practice, we can approximate beta star by using a sample covariance, at least for large M. Okay? Remember, beta is the optimizer, and in the optimizer, you have a very flat region. So perturbing around it doesn't make too much of a difference. And you can still allow for errors there, and you still have a very nice variance reduction. All right? So it's very insensitive. It's a good method in that respect. Okay. Any other question? Yes?
Does it make any sense to iterate this procedure? Like you're trying to find more than one random variable?
Yes, that's an excellent question, actually. So two things to say here. Suppose that we were computing this expected value of q of y, q of u of y, right? And these y's were random variables. And were Gaussian, for example. So for this vector of y's, now y is a vector, right? So it's y1 up to say yn. You know essentially all moments for any polynomial that you can make out of these random entries, because they are Gaussian. So you know essentially by hand all the moments. Okay, so you can use this very effectively. You can try to have another function that is a function of this vector to approximate this q, right? So the difference of the variance is very small. So you, for example, I can just say the following. You can just use now a beta vector times the entries of y. Okay? This now has n entries, and you have to find n entries for the beta, right? And you can find them by this covariance formula that I told you. So you have like n control variates acting on this quantity. And this is just if you include the linear terms. You can include more if you want to. All right? Does it make sense? So in multidimensional situations, you expect actually to use this to your advantage and have more entries than just one. Okay? But you know, the word iterate comes also in this context, but with another meaning. You can say the following. We're computing y, and we used x, assuming that we knew exactly the expected value of x. This makes sense in this context of y entries, right? Because they were Gaussians and all the moments are known. But you can say the following. Suppose that actually, instead of having an x for which we know the expected value exactly, we have an x that is much cheaper to sample than y, but for which we do not know its exact mean. Would that make the method unusable? Remember, we started by saying, I want to compute the expected value of a certain random variable y. I assume that I have an x that is cheap to sample, right? And I know the expected value of x exactly. So I summed and subtracted the expected value of x, and I went from it. Now I say, suppose that I do not know the expected value of x exactly, but x is still very cheap to sample. Can I still use it to my advantage?
If you know
Yeah, exactly. So I don't know if I can erase something here. Let's see. So So before we said we sum or subtract something, right? So we said expected value of y was approximated by the expected value of y minus, say, beta x plus expected value, and there's a beta here, of x, right? So now I can just use Monte Carlo in both, like you were saying. And I approximate this by 1 over m1 sum over, say, little m1 from the 1 to m1 of y minus beta x. I sample them together, right? Omega m1 here. And then plus 1 over m2 sum from m2 equals 1 to m2 capital of x omega 2 m2. And these samples are independent of these other samples. When I go and compute the variance now for this estimator, I have to sum the variances. I can optimize with respect to M1 and M2, and you will see that you have an advantage. Provided, again, X is sufficiently cheap to estimate, and X is sufficiently correlated to Y. Okay? And now you say, okay, why should I stop here? If I have another guy that is actually close to X and is cheaper to X, I can have a third term, right? And I can keep going, right? So I can have a cascade of x's, right? One trying to reduce the variance of the previous one, right? And then you say, okay, but this looks really abstract. Why do I care? I mean, it doesn't make any sense. Do we know a situation like this that comes super often to us when you do, say, numerical discretizations? That is far from being abstract and is actually commonplace. What would play the role of y, and what would play the role of the x's? When I tell you, it's just a joke, but I want to see if you find it. What do you do when you solve a PDE? How do you actually proceed? You start with a coarse mesh, right? Correct? And you try it. And if you're not happy, what do? You just go home, or what do? How do you improve it? Say. You refine the mesh, okay? And now you get another approximation. And what happens with that approximation? It's more accurate. But it may not be enough. And if it is not enough, what do? You go home. No, you do something else. Okay, what do? You refine, right? And now you create another whose cost per sample is more expensive, but is more accurate than the other two. And so on, right? Until you actually hit one level where you say, oh, I'm happy. The discretization error here is below my accuracy prescription. I can stop here. And that's what you usually do in the deterministic computation. You stop here, and you don't look at the other guys that were above, because they're useless. But in here, they're not, because each of them costs less than the previous guy and somehow is close to it. So they can be used as control variates. So you can have a solution that was xh, right, that was accepted, and you could use x2h, meaning that you were using double the mesh size, as a control variate for xh. And x4h could be used as a control variate for x2h, and so forth and so forth. With xh, and where do we stop? Well, you can use all the meshes maybe that you started from to work with. And eventually you're going to be able to pass a lot of realizations from the very costly mesh that you found to satisfy the discretization bias to the ones that are really poor and you could not have used them to do the real computation. But from the statistical point of view, they're very, very useful. Okay? So this sort of cascade of x's is not far-fetched. It's actually the commonplace. Every day you see them in numerical analysis. Yes?
You want to dig into the sufficiently correlated question?
Yes, we are going to go a little bit beyond that, actually. We're going to show the complexity of this kind of cascading method, which is a multi-level. Hopefully, if time allows. Okay, so I hope the idea was clear. This is the preamble to Multilevel Monte Carlo. Let's do Multilevel Monte Carlo. So the context is the same as before. We want to compute this, but now I assume that I have at my disposition all this hierarchy of meshes, because I've been trying them. Okay, I'm saying I have a hierarchy of meshes, x, h divided by 2, h divided by 4, and so forth. And what is the property here? That as h goes to 0, we have a proper convergence in the right space, and the cost to evaluate this guy blows up. Right? Before we assumed h to the minus d gamma, I will keep assuming that just for clarity. All right? Each PDE we have a different model. Okay, but for the linear ones that I gave you, this is the right one. So we have a sequence of meshes that we have been trying, right? And HL capital is the one that we are happy with, but in the process we have created all these others. Now, this is a notation that I have. I mean, this g of omega was the quantity of interest applied to the u, the exact solution, right? So this is the exact quantity I'd like to compute the expected value of. Instead, I have these approximations that are based on meshes, okay? And the computation now, instead of computing this, is just to compute the expected value of GL, because the HL was the one that had sufficient bias. You know, the bias was below the tolerance. So that's what I want to compute. So what's the main idea? You just rewrite this guy as this telescopic difference. This is a telescopic difference, and there's an equality here. So I have not lost anything from the left to the right. And now what happens? Well, the multi-level Monte Carlo, instead of taking a Monte Carlo average of this guy, it takes L capital plus 1 sample averages for each of these terms appearing here on the right. That's what it does. And it does it independently, so you use independent samples. All right? So that's how it looks. Monte Carlo for the first term and Monte Carlo for the L other terms. Notice that we have not changed the bias of these approximations, still by the telescopic property, the expected value of the GL. So we are just reducing the statistical error, hopefully. So to simplify the analysis, we just consider the mean square error, and the mean square error is just the variance difference here and the bias. So let's look at the variance. The variance, again, we have the sum of independent quantities, and this corresponds to the variance of the sum. This the sum of the variances, sorry, and for each of these terms, we have a Monte Carlo-like type of variance, you see, divided by M0 and divided by ML. What is interesting here is the following, that we have a convergent approximation. As L goes to infinity, GL converges to G. Otherwise, we don't have a consistent method, right? Is that clear? Okay. So if GL is converging to G as L goes to infinity, the same happens with GL minus 1, meaning that the difference between GL and GL minus 1 is going to 0. Okay? And in particular, the variance of GL minus 1 is going to 0. So this term here is going to 0. So to make this quotient small will become cheaper and cheaper in terms of ML samples as L goes to infinity. And that's crucial for this method to beat really much Monte Carlo, because when L is large, these evaluations are extremely costly. Right? And what this is saying is that you're going to need to sample less and less in the levels that are very costly. Okay? And this is what I just say here. Okay, so there's just not much to add to what I just told you. Okay, and a little bit more intuition here. How does the statistical constraint look like? Well, in the Monte Carlo, we remember we have to satisfy a constraint that looks like this, right? That we have a single level, that was the deepest one, there was the variance divided by ML. The variance essentially is approximately the variance of G. So essentially this is constraining ML capital by tau to the minus 2. Yeah? So essentially you need, in the deepest level, tau to the minus 2 samples. If you do multi-level Monte Carlo, on the contrary, only the first term looks exactly like this, But the others have the variances of these differences, and these were smaller than this thing because they're variances of differences, and the difference may be small. Okay? So at the end, when L capital, when you reach little l to be L capital, you're having a very tiny number here, so you end up having an ML capital that is way much smaller than this. Okay? So effectively, you're passing samples from a very refined mesh into a much coarser mesh. That's what you're doing. All right? Now, this can be quantitative. This one can be quantified, but you need assumptions. So let's go through the assumptions. We need to assume essentially assumptions with respect to cost and convergence rates. So C0 is the cost of generalization of G0, CL is the cost of generating this pair, GL minus 1, and VL are the variances of the differences. So the total work, as we did in Monte Carlo, will be a decomposition of number of samples on each level times the cost of the average cost of a sample in that level. Okay, so that's trivial. ML, CL. The variance, as I told you before, because of the independence, is just a sum from 0 to L of VL divided by ML. That's because of the construction. We constructed independent samples, and this is what it gives you. Now we optimize with respect to the M's, and we say we want to find the M's so that the total work is minimum subject to the statistical constraint to be less than tall, meaning that the variance of the estimator is less than tall square. Okay, so now this is a simple problem to solve with respect to M's. You solve it explicitly, that's the answer. So each of the M's is proportional to 2 to the minus 2, but this quotient, which is the variance divided by CL, is going to 0, possibly relatively fast, as L goes to infinity. Why? Because the variance of the difference is going to 0, and the cost is going to infinity. So you have something that goes to 0 divided by something that goes to infinity. That's super 0. Okay, so this is going to 0 relatively fast. And then here you have this other sum that may or may not blow up, essentially. Yeah. So, but I mean, here, so far I was considering L fixed. Let's go to that later. All right, so we go and substitute. I mean, we do the same, Lagrange multipliers argument. And we go and substitute into the optimal work, and essentially we get the optimal work to be this. Tall to the minus 2 times this sum, and then something that doesn't depend on tall, so we just disregard, essentially. So we have this thing here. Now, what happens here, essentially, this is a variance of the difference. This is going to 0, and this is a cost per sample. This is going to infinity. So you have a product between something that goes to 0 and something that goes to infinity. You take a square root. Anything can happen here, right? They are positive quantities, so this product could be such that this sum, as L goes to infinity, becomes finite or is infinite. If this is actually bounded uniformly with respect to the L capital here, this work of Multilevel Monte Carlo will be bounded by a constant times tall to the minus 2. Okay? But remember, now we are solving PDEs. And we have to meet a bias constraint. So when the bias constraint becomes more and more stringent, the H has to become smaller, right? So the cost per sample in the deepest level goes to infinity. Still, if this is convergent, you get the complexity of Monte Carlo when each of the samples costs you 0.01. So if this doesn't surprise you, nothing will, actually. Okay? So I'm telling you, I'm refining more and more the solution of a PDE, so the cost is blowing up, but I still can reduce the complexity, if this sum is finite, to the case of Monte Carlo, where you know the exact solution, essentially, and the evaluation of the exact solution costs you 0.01. Is that clear? And then you can wonder whether this actually happens or not. And actually it does happen. We have conditions for that. I will show you the conditions. But it's not an empty case, actually. It's the magic case that I call the magic case. All right, so let's go a little bit more into it. So assume that you have geometrically distributed hierarchies. So essentially this delta now is a constant that is less than 1. For example, 1/2, meaning that you're subdividing by half each of the elements when you go from one level to the next. And in terms of that, you have a deterministic error in terms of the mean that is of order alpha. And for the variance convergence, or second moment if you wish, you have a convergence rate that is beta. If you have a smooth problem, beta will be 2 times alpha in this context. If you don't have a smooth problem, they are not related that high. The cost is still h to the minus d gamma, right? And the same assumption as before holds. Yeah, these are other things. We don't need to discuss that. This is the result. So the result says the following. The magical case actually happens when the rate beta of a strong convergence is strictly larger than the exponent of the work d times gamma. Okay? So I go back one step so you can actually see it. Beta was the rate by which GL approximates G, or GL minus 1 and GL actually converge in this square sense. Okay? If this beta is larger than this d gamma, okay, that series that I was talking about is convergent, and you get this magic case where the work is as if you don't need to discretize the PDE, or equivalently, somebody's giving you the exact solution and you can evaluate the exact solution with cost 0.01, all right? And that makes a difference with respect to Monte Carlo, right? So it removes entirely the other term, the d gamma divided by alpha. So if beta is not actually larger than d gamma, you have a limit case here where you have a log deterioration. If it is less, you still get something better than Monte Carlo. Remind you what Monte Carlo was. So you have d gamma divided by alpha. Here you get a reduction from d gamma to d gamma minus beta. That's what multi-level gives you. So if you do this cascading effect, it's not just a matter of multiplicative constant. You change the exponent and the complexity. Okay? And that really matters. Any questions?
So in both cases, Monte Carlo and multilevel Monte Carlo, you still have this D, so you could still call this the curse of dimensionality, right?
Yes, the curse of dimensionality is not the curse of dimensionality we discussed with respect to the integration. It's the curse of dimensionality in the numerical solver. Right? So we're talking about D not being 100, but D being 3 or 4, because you're solving a three-dimensional problem plus time. But this D will not, the D that is there will not be 200, right? Will be the usual PDE solver.
So it's not as bad.
It's not as bad as the other. It has a curse of dimensionality with respect to this D, but it's not as bad as the curse of dimensionality with respect to the integration. But multi-index Monte Carlo actually attacks this D. Okay, so multi-index Monte Carlo, what we'll do is to remove this D from this discussion and have just beta larger than gamma. That's what we do in multi-index Monte Carlo. So it will be a little bit more dramatic, but we are not yet there. Okay, so this is the proof. We don't need to go through the proof. I just have it for completeness. So there are two cases that are worth discussing here. One was the case where beta is larger than d gamma. This was this magic case, right? Where essentially you transform the computation of a stochastic PDE into just a stochastic problem, trivial problem. There's another case, and it is this essentially, this case, where actually the beta is actually equal to 2 alpha. This happens for smooth problems. So in smooth problems, you have a rate of convergence for the mean that was alpha, and then if you take a square here, you get 2 alpha. Okay? For smooth problems, you expect that to happen. Okay? So beta in that case will be 2 alpha. But there's a nice cancellation in that case, because this beta divided by 2 alpha is 2, and this cancels these 2, which is, oops, I mean, what happened there? And the only thing that you get essentially is told to the minus d gamma divided by beta, divided by alpha. But told to the minus d gamma divided by theta, told to the minus d gamma divided by theta, is essentially the cost to solve one PDE. So essentially, you started with a stochastic PDE, and Multilevel Monte Carlo brought the complexity to a deterministic PDE. So you got rid of the cost of the stochastic approximation. So in one case, you get rid of the deterministic cost of solving the PDE, and in the other case, you get rid of the sampling cost, right? So in one case, you know, stochastic PDE, in one case you remove the PDE, or in the other case you remove the stochastic part, all right? So it's magic on its own also, all right? Any questions? No?
Yes, maybe. For the last comment you made, so we get rid of the stochastic part, meaning that now, for the case that you have a random field as no input, so we get basically...
You will get a complexity that will be as if your problem is deterministic. It won't be. You will do stochastic computations anyways. But when you go and look at the elapsed time in terms of the accuracy, you will feel that you're solving a deterministic problem for the same type of PDE. Crazy, right?
That sounds like magic.
Yeah. Okay. So the two cases are magic actually. So if you don't get surprised or upbeat by this, you just wait until the other part of the talk and then you will. Okay. So let's go. This is not the proof. I put some references now because there are questions to be answered in this context. We assume, for example, that these meshes were geometrically distributed. Why? I mean, it was a natural assumption if we go from this sort of trial and error mesh refinement, right? So you have a uniform mesh, and then you don't like it, you divide by 2, you don't like it, divide it by 2 again, you don't like it. That creates a geometric sequence of discretizations. But now you're in the mood of, let's optimize the work with respect to the parameters so that the error is less than something. And then you say, okay, but this geometric distribution was a choice that looks ad hoc. Why would we use that and not something else? And the answer is yes. If you go and optimize, you do not get a geometric distribution. You can also analyze the behavior of the adaptive Multilevel Monte Carlo, and there's another question. It's like, in this computation of Multilevel Monte Carlo, if you want to do this practically, you have all these issues, right? The optimal number of samples is a function of the cost per level times the variance of the difference. And these two things are not given to you as input parameters. The input parameter is the writing of the PDE and the input distributions to your random fields. So if you really want to solve optimally this, you need to learn these variances on the fly and the cost on the fly, right? And you need to ensure that this learning phase, or whatever you want to call it, does not become larger in cost than solving the problem itself. Otherwise, you killed Multilevel Monte Carlo. I want to emphasize a little bit more what is going on here. The number of samples essentially gets smaller and smaller and smaller as you go deeper into the levels, right? Because of this is going to 0, this is going to infinity, so this is going really, really to 0. Okay, but that's scary. Why? Because you have less and less samples available to you. And this means that you're doing sample variances, for instance, to understand the VL. This statistically will be less and less robust. But this is crucial because this is a crucial question because the deeper levels are the most costly ones. So if you screw up the estimate in the deepest level, you very likely screw up the whole computation. Okay, so you have to really be careful in estimating these VLs. Otherwise, you lose control on the computation altogether. Okay? So that's the motivation for creating these algorithms. In this case, the continuation Multilevel Monte Carlo that on the fly understands the VLs and the CLs without actually having such a big impact in the computation of the problem you want to solve. Okay?
Sorry, we calculate also need to do this telescopic.
Yes, this is telescopic as usual, but the telescopic is the mean. You want to understand the variances. because the variances determine the number of samples.
But can we construct it also for variance?
Yes, you can construct a multilevel Monte Carlo for the estimate of the variance, but still, how many samples do you have in the deepest level? Not so many. So even if you do that, the problem is still there. Yes, the problem is still there. Actually, we do use, the multi-level for the variance as well to improve the thing, but you have to use more and more things. Essentially, what happens is the following: in the coarsest levels, you will have a huge amount of samples. In the deepest levels, you will have very few. So you try to create a Bayesian type of model that, based on what you learn from the deepest levels, you predict what is going to happen in the deepest ones, and you enrich this with the few samples that you have. So that's how you go around it. There's no magic, really. Okay. This is an example. That's the example that I gave you before. What am I trying to do here? I'm trying to motivate the optimization of the parameters. Okay. So which are the parameters you are trying to optimize? We are trying to optimize the MLs here and the H's. So before the H's were fixed and we were just trying to optimize the M's. Now we are trying to optimize the H's as well. Okay? And now we track all these constants that before we didn't track. Now we're going to track the QW, the QS, not just the exponents here. Okay, so one can actually solve this problem. It's a little bit of a pain, but in terms of these quotients between the strong rate of convergence and the growth of the work, the weak rate of convergence and the growth in the work. So you can actually write this problem, optimize how much of the error you put into the bias constraint and how much you put into the statistical constraint. You solve everything, of course, assuming some normality, but you have to show. So I don't stop on that. Poop, poop. Okay, so the level L that I didn't discuss too much before is immediately determined by the bias constraint in terms of tall, as essentially log of tall being proportional to h. That's essentially what you get. And now once L is fixed, you try to optimize the M's and the H's. So this is a continuation, but I wanted just to show you the algorithm. Poof. See? No? Okay, so these are the error plots that you can actually have when you run this algorithm. Here's the tolerance you want to impose, and here's the actual error that you get out of your algorithm because you have a reference value. And what you want to do is to run this many times, right, and ensure that you run, for example, 100 times. Only a certain percentage of those times you will exceed the tolerance you prescribe. That's a confidence level. Okay, so you do this for several tolerances and you keep track of these occurrences. And in this case, we were using a 95% confidence. In one case, we were using an iterative solver, and the other a direct solver for the same PDE, namely the linear elliptic that I showed you at the beginning. And this is just to convince you that actually you can actually compute learning these parameters on the fly and don't get too much of an exceedance in the cost with respect to this magenta line, which is actually the cost that you would incur if you know exactly all the parameters, the VLs and the CLs, to solve the problem, that are needed to solve the problem with optimal cost. Okay, so there's not much of a change in one case or the other. Let's see. Okay, this is what I wanted to get to. And I don't want you to get scared, it's just to have the message. If you are in the case where the rate of strong convergence and the rate of explosion in the work are equal, then this chi is equal to 1. And then in that particular case, you get a geometric hierarchy. But this beta that is here is a particular number and is not 2 or things like that. You have to find it. And this theta that was splitting between the statistical error and the bias error is not trivial. Namely, as the tolerance that you prescribe goes to 0, this theta goes to 1. Essentially, most of the budget of the error goes to deal with the statistical error, and only a very tiny fraction is left for the bias. Okay? That's not what you would expect at the beginning, but it's really what you have to do. Okay, and now when this chi is different from 1, the whole thing is much more complicated, but you can still track all the parameters. In this optimization, you recover the classical rates of convergence. These are the classical rates of the 3 regimes, the magical one and the other thing that I told you. But you now can get explicit constants in all these cases, C0, C1, C2, in terms of the input parameters that you have in the assumptions of variance, convergence, and work. Okay, so this is very explicit and can be written down. Why is this important? Well, you may understand in the different regimes which of the constants is actually relevant, and then you can understand if you play a certain trick to reduce or to do something at a certain level, whether it is going to make a difference or not. I'll just give you one example. In this C2 case here, this V0 plays a role. So if you do a trick to reduce even further the cost in level 0, this will pay immediately. But if you are in these other two regimes, it won't. Okay? So tracking the constants also matters. I told you that this beta was not trivial, right? And you can see it here. This beta, when you are in the case chi equals 1, has an explicit dependence like this, and the k in the chi different from 1, you can have a nearby geometric distribution of the h's that performs quite well, but it's not the one that you would usually take, like divided by 2, for example. It has a dependence on all these parameters that define the problem. Okay? So the spacing really matters as well. The spacing of the h's, that's what I mean. Okay, so let's see. Yeah, I discussed Multilevel Monte Carlo, and I don't think I should dwell too much into this, otherwise we're not going to get into this. Okay, now the question about D. This is Multi-Index Monte Carlo. So what was the game? Essentially, we said that to apply these ideas of variance reduction, we needed to have computational approximations that were close to the one that we want to use, and each of them cost less, right? And then taking this difference, we were able to pass realizations, so to speak, from the costly ones into the cheaply ones. Yes? Okay, and we said that what we were trying was a mesh, right? And we were not happy, and then we created this mesh, and this was sufficient, and then we have two meshes, and then we play this multi-level game. And if you have an isotropic problem, essentially a problem where all dimensions behave in the same way, you will tend to refine them, all of them in the same way, right? Because, I mean, there's no point in having an isotropic refinement if your problem is isotropic, correct? Yes? Okay, but this is not the game we are playing here. Because the game is to try to find guys that are close to this, and they are just cheaper, right? This is one of them. Can you tell me another one? Can you tell me another one? That is close to this and is not exactly this mesh. It has to be cheaper, it has to be close to it. And actually maybe even closer to this than this. Yeah, exactly. We have two more at our disposal. These are the ones that you don't usually use because the problem was isotropic. But from this perspective of variance reduction, this is close to this, and this is cheaper to work with than this. So this is a good candidate as these two. This is a little bit more costly than this, but it's closer, so maybe it pays. So now instead of having one guy, we have three. How do we put them together? Now your question about having several to reduce the variance. to get a better rate. And will it pay? Maybe it doesn't pay, because maybe there's more work, and maybe it doesn't pay. So, to go in this direction, we need to introduce anisotropic refinement. So how do we do that? Now we say, instead of having one H, we have D dimensions in space. Each of them is going to be refined by a different parameter of discretization. So we called HI such parameter. And we say that HI is essentially HI0 times something that is beta I to the minus alpha I. So beta I, just think of 2, right? And just think, okay, alpha I is 1, say, I refine 1 times, alpha I is 2, I refine twice, okay? So if you fix the numerical approximation, namely you're using a certain type of finite element, and you fix the vector alpha of alpha i's, your numerical discretization is uniquely defined. Is that clear? Right? Because you have determined in each of the directions how much you refine. So there you go. You have an anisotropic approximation, just one. But it's uniquely defined. Okay? And now that you have these discretizations at your disposal, you create one-directional differences. So essentially, this difference here is the difference of the G alpha that was computed with this alpha minus the G alpha where you de-refine only along direction I. Exactly this picture, right? This will be a de-refinement along the Y direction, and this is a de-refinement along the X direction, okay? This is exactly what is here. It's the approximate solution minus an approximate solution that is one level coarser in direction I. The rest is kept as constant, okay? And now that you have these deltas, right, along all the directions, you compose them. So you take a difference of a difference of a difference of a difference of a difference d times. This is a mixed difference of order 1, right? And this is a type of difference you are very much used to compute mixed differences of derivatives, right? When you take a derivative in direction 1 and 2, you take a difference along direction 1, and of that result, you take a difference along direction 2. And you get 4 values essentially, right? 1, 1, minus 1, minus 1, and then divide by the h squared, say. Okay? Here's the same. Okay? This stencil, if you wish, in the plane of the alphas, contains 2D evaluations, but only one vertex is really the costly one, right? The one that has all the refinements. The other are kind of geometrically de-refined and they don't cost in comparison to the other. So you don't have to be scared by the fact that you have 2 to the D terms there, because one of them is the dominant. All right? Okay, you may say, okay, but this looks very, very restrictive. You are using this tensor type of approximation. Maybe the domain has to be a tensor. Not true, okay? So you have a lot of flexibility in these constructions. I'm not going to stop into this, but it's not true. I'm just presenting this for simplicity. So how does this look like? I told you, you take a difference of a difference. So the stencil in the alpha 1, alpha 2 plane will be like this, right? This will have a plus 1, minus 1, minus 1, essentially what you have there, okay? And now you build the multi-index estimator that will look deceivingly close to the multi-level, but it's not the same. So let's see. We are assuming that we have consistency in our approximations, namely when when alpha goes to infinity, G alpha converges to G. And by that we mean that the minimum entry on this alpha vector goes to infinity, right? Otherwise we don't have a method, and we are just talking nonsense, right? So we have to assume that we have consistency. That's the first thing. Now, second, once we do that, we realize that we can rewrite, and this is an equality, the true quantity by a sum of the differences, the mixed differences that I wrote before, over all alphas in the lattice n to the d. This is an identity. There's nothing lost here. Okay? You can write a function as an integral of the mixed derivative. You can do that as well. So there's a continuous version of this. But now what you do is the following. Okay, I don't want to pay for all the indices, because as alpha goes to infinity, this becomes very expensive to compute, and each contribution is very small. So I truncate it. Instead of working with n to the d, I introduce a calligraph I set, and I work with these finitely many alpha multi-indices. And now I say this set I is properly chosen, and we're going to discuss that. In multi-level, we only needed to introduce the number L capital. Remember? Level 1, 2, boop, 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 until in level L capital you get the bias under control, and that's your approximation. Here you have a set of lattice values. It's not just a number, right? You need to define the shape. You have to do it optimally. Otherwise, we cannot play this game of minimal work for a given accuracy. Okay, and once you're here, you just apply Monte Carlo as you did with multi-level, and you get this estimator. Sum over indices, and then Monte Carlo for each of these quantities. All right? So now we have to choose the M alphas in an optimal way. That will not be difficult at all. What comes new in this context is the choice of this I. So the same game as before, we want to satisfy the total error less than the tolerance, and provided with a certain confidence level. We split this into a variance constraint and a statistical constraint. The statistical constraint, using a central limit type of result, you approximate it by a variance constraint. It is much easier to deal with. And you work and obtain the optimal M alphas, substitute into the work, and you get this dominant term, where again you have 12 to the minus 2 and a sum. The sum now can be either finite or infinite. If it is finite, you get again 12 to the minus 2, which is the magical thing as in Multilevel Monte Carlo. If not, you have a deterioration, and you have to analyze which type of deterioration you get. Clear? Yes? So again, it looks deceivingly close as before, but we have to decide what is the I now, because once you substitute the optimal M's, the work depends on I only, and this is why I emphasize here work of I. So we have to choose the I optimally to achieve a certain bias with minimal work. If you just use trivial choices like a full tensor type, you don't get optimal complexity. So the question is the following. You have to minimize the work with respect to the choice of I, such that the bias, because remember, we have chosen the M's, so the statistical constraint is already satisfied. So we only need to satisfy the bias now. Such that the bias, which is the sum of the complement over the complement of these contributions, is less than total. Okay? Fortunately, this problem looks very much, after you take, instead of the work, the square root of the work there, like a knapsack problem in classical optimization. Okay? And then for that problem to be solved, you have to create the profits, essentially, which are the quotient in here of the bias contribution versus the work contribution, and threshold them. Essentially keep those alphas such that this profit is larger than a given threshold. That is the shape of the optimal sets for approximation, I calligraph. So if you change the problem, you change the method, you change the numerical, linear solvers, things like that, these quotients will change, and the shape will change accordingly. Okay? So this shape will adapt to essentially any problem you may have. And in order to use multi-index Monte Carlo optimally, you need to understand what is the shape of optimal approximation. I'm going to give you one example now, but it's just one example. Don't believe that this is a general theory, because the general theory always goes back to the profits. Okay, so there's a connection with the sparse grids in this context as well that I'm going to discuss, but the optimal profits that I told you come from the thresholding of the profits. There are results on that. And now, what is the generalized framework? As I told you before, once you know the shape of these I's, which essentially says threshold the profits, you can find from that family, as a function of toll, the one that the smallest set of that family, right, such that the bias constraint is fulfilled. Okay, so you have the optimal shape, and then you stop where the optimal, where the bias constraint is fulfilled. Once that that bias constraint is fulfilled, you go and substitute this I toll on the work formula that you had before, and now you have the optimal work for multi-index Monte Carlo, which always is bounded below by toll to the minus 2, and now depends on this sum being finite or infinite as toll goes to 0. All right? And so you expect to have a p here that could be 0 in the best case or larger. Okay? So let's see. We're going to make assumptions now that are reasonably many problems, but the nice thing with these particular assumptions on the profits will be that you can relate immediately the results of multi-index Monte Carlo in terms of the complexity results that we saw before for multi-level Monte Carlo. So we assume now that the bias constraint, the bias convergence happens so that when you take expectation of this mixed difference, you get actually the product of the errors in all the different acting directions. Now I ask you, is this a reasonable assumption or not? Let's take one step back. If you're taking the mixed difference, the mixed difference to approximate a mixed derivative, what do you expect the mixed difference to become? Essentially, you have delta 1 acting on delta 2 of f, right? That thing is supposed to be bounded by, say, h1 times h2 times the mixed derivative of f. And if the mixed derivative of f is bounded, you get a constant times h1 times h2. You get the product, right? In here, you're assuming the same, okay? And you can actually verify for certain problems that this happens, even in non-trivial ones, like stochastic particle systems. So this happens for the expected value, this happens for the variance, and for the work it's actually trivial because you just tensorize the work, and this is not different from the h to the minus d gamma that I showed you before. Okay? So the really new thing is happening here, not here. So if you go and now substitute these assumptions into the work of Multi-Index Monte Carlo, you get these sums, right? You go and optimize the m's, and well, this is just the thing. So you go and substitute and put the profits in terms of these assumptions, right? And you get this wi plus gamma I minus si divided by 2, and then multiply times the alpha. And then you realize that the optimal set now is linearly constrained in the alphas. So you have a hyperplane, essentially, this picture, that may be tilted actually, right? That is constraining the alphas. So the optimal set is below this line, all right? And this tilting contains all the information about the convergence and the work, essentially. It's affected by the weak rate of convergence, the strong rates of convergence, the work convergence, right? And this is just a normalization constant. And this is just the discretization refinement parameter along the direction I. Okay, so all the ingredients actually come into the construction of the optimal set. And now comes the question. Now we know the optimal set for these particular assumptions in the multi-index Monte Carlo. What is the corresponding complexity result? And does it compare in some way with multi-level? Yeah? Okay, this stuff is the general result. I'm not going to stop at it. I'm going to look at a particular case. What is the particular case? The particular case, oh, this is a rough. Let me take it smooth. Okay. So let's take a case that is really fair for comparison. We take an isotropic problem. No direction is particularly relevant. So in principle, you should refine all of them in the same way to get accuracy. So there is no advantage for multi-index Monte Carlo to exploit one direction and say, okay, you should refine less in this direction because it's less important. All of them should be the same, okay? And we'll see if we get an advantage. So we assume that all the rates are the same along all directions, right? The SI is 2W because of this smooth behavior of the solution, as I told you before. The beta I is the same, so you're refining this in the same way in all directions. The work rate is the same because maybe you're solving a coupled system. And D is larger than or equal than 3, okay? Really, the tough problems that you want to solve in practice. Remember, the work in Monte Carlo was told to the minus 2 from the samples, told to the minus D gamma divided by W coming from the solving of the PDE. In multi-level Monte Carlo, you have the optimal case when 2W is larger than D gamma, right? And in that case, you get told to the minus 2. So essentially, the weak rate has to be larger than D gamma. So if you're using, say, something that is in 3D, and then something that is not optimal, say 1.5, okay, this will be 4.5. So at least you need something that is, what, order 3 at least, okay, to be in this case. But if you have multi-index Monte Carlo, and you have the assumptions that I told you before, you only need 2W larger than gamma to be in the optimal case, not d gamma. Now that can be a big deal. And if you go to this other magical case where you actually go from a stochastic PDE, because you have the number of samples told to the minus 2 times the cost per sample, into something that was a deterministic part, right? You see, you get only this exponent, right? You get rid of the stochastic part. In this part, essentially, you get, again, rid of the stochastic part, and up to log factors, you get a problem in 1D. So you started with solving a PDE that was stochastic in D dimensions. You brought it back up to log terms into the solution of a deterministic PDE in 1D. And by the way, you remember, we were solving everything with the same finite element code, just with anisotropic meshes. There was no rewriting in the finite element code, as long as the initial code was anisotropic. We only changed the way we sample the solutions. So in terms of work to rewrite this, it's just the work of the sampling, not of the solver, provided the solver was anisotropic. Is that clear? Okay? Yes, please.
Would it work in the same way if you had unstructured meshes instead of
I made this thing, for example. So you may have these type of things that are a little bit structured, or you may have a combination of unstructured and structured. So in this case, for example, the dimension in the space that you're working is 3. But the dimension in multi-index Monte Carlo is 2, because in this way you're refining the unstructured mesh, having a single mesh size, and in the vertical direction you have another one. You're tensorizing 2. Okay, so I didn't spend time into that, but the dimension in the parameters of multi-index Monte Carlo does not need to be the dimension of the physical or time dimensional space. It could be something else. Okay, you could have a dimension 3 in physical space, and maybe you have a dimension 5 in multi-index Monte Carlo because you have other parameters to play with. This can happen, okay? And if you have multi-scale problems, this is even more dramatic, actually, because you have small mesh size, big mesh size. You can be anisotropic with respect to 2, and you can actually go easily high dimensional with respect to multi-index Monte Carlo. But provided that you have this nice mixed regularity, the guy will not be affected by that D. Will not be affected by that D. So you have the luxury to go up, actually, because you're being sparse with respect to it. Okay? Okay, so essentially what multi-index Monte Carlo is doing is bringing the computation of multi-level into 1D computation, complexity-wise, if you have the right assumptions. Okay, so you say, okay, this looks great, but rates are good, but constants are also important. So what happens if multi-index Monte Carlo has this very nice rate, but the constant in the error is much larger? This will not give me much, right? So what happens actually in practice? Let's do some computations. So in this case, we take a 3-dimensional PDE where we have a solver that has gamma equals 2, so it's not optimal, and we are using piecewise linear tensorized finite elements, so the W is equal to 2 and the S is equal to 4. This is a smooth problem. PDE in 3 dimensions, and the coefficients are actually driven by 2 random variables in here. This was important to get a reference solution that was not coming out of this method. It's not really coming as a constraint for the method itself. In the numerical test, when we compare methods, you always make sure that the error levels are comparable, because if you're going to claim that something gives you less work than something else, you better make sure that the error that they're both given is comparable, right? Otherwise, you could make one error much smaller and the work will be much larger. Is that clear what I mean? You're comparing two methods now. You have to make sure that they both give more or less the same error. Because then when I show you the accuracy versus work plot, it will make sense. Yeah? So again, here's the tolerance I impose. This is the error that I get. And I'm showing the behavior of multi-index Monte Carlo with the optimal set, which is this total degree, a non-optimal set, which is full tensor, and multi-level Monte Carlo. All of them for the different, for the same problem. First thing you see is an advantage in memory. So the largest problem that you have to solve in this sampling for a given amount of accuracy in the problem is much smaller in the multi-index Monte Carlo than in the multi-level or the multi-index Monte Carlo with the wrong set. Okay? And this is not minor. I mean, this could be a huge difference in terms of memory. That's one thing. The other thing is the computational work. So in this thing, for the three-dimensional case, multi-index Monte Carlo still attains the optimal rate, which is 10 to the minus 2, whereas multi-index Monte Carlo with a non-optimal set or multi-level Monte Carlo, they both go into this 10 to the minus 3. So the message is, be careful when choosing the optimal set for multi-index Monte Carlo. It's not guaranteed that you're going to get the optimal rate for any set. That's not true, okay? So you have to be careful to follow this recipe of thresholding the profits. And the constants are essentially the same, okay? So really the rate is telling you the story. Now, we don't plot here, but if you believe that you're clever, right, and you're just going to sample the outcomes that your PDE solver gives you, you will be doing Monte Carlo, and in this context, you're going to get a complexity that is 10 to the minus 5. So it really pays to sample differently. So you go with the same finite element, essentially, from 10 to the minus 5 to 10 to the minus 2. That is less than square root complexity. Okay? So this is the difference between being able to solve the problem and not being able to solve the problem. Okay, and if you go to 4D problems now, this thing is still showing 10 to the minus 2, where this now multi-level Monte Carlo jumps to 10 to the 4 and to the minus 4. And if you were, again, trying to be clever and just using Monte Carlo, you get 10 to the minus 6. That's, cubic root advantage. Okay? And one has not changed the finite element solver. It's just the way you sample. Okay, so provided that you have the mixed regularity, multi-index Monte Carlo will work better, right? So you have to verify that your problem either numerically or theoretically satisfies this constraint. You have a general analysis framework based on the optimal sets and that come from the thresholding of the profits. You have other cases where the MIMC direction is not like a special direction. I gave a talk a few weeks ago here showing you the use of multi-index in stochastic particle systems. And you can use this for inverse problems as well. Okay, so now I have some time left, and we can try to dwell into multi-index stochastic collocation. What is the point here? The point is the following. In multi-index and multi-level Monte Carlo, you have this type of results, and you always have here the lower bound 10 to the minus 2. I mean, maybe here it's not so easy to see it, but in here it's obvious, right? The work will be 10 to the minus 2 times something else. Okay? This something else may or may not depend on toll, but if it depends on toll, it's blowing up. So you're not going to get a lower, you're not going to go below 10 to the minus 2. This comes from the fact that you're sampling with Monte Carlo. Okay? And you can say, okay, but we know other ways of doing samples, right? I mean, this is a deterministic type of sample, and we know it doesn't perform well when you go up in the dimension, but maybe using a sparse quadrature that is a little bit more clever than this, we can beat Monte Carlo. We could use also quasi-Monte Carlo, that is not Monte Carlo, but exploits regularity and get a rate that in terms of the number of samples, it's morally close to 1, okay? So n to the minus 1. Instead of n to the minus 1/2, morally gets to n to the 1. But you could go even beyond that, right, if you have available regularity. And that's what I touched here upon briefly in the last part of my talk. So what's the idea then? Whenever you have an expectation, you use a sparse grid type of approximation. You use a deterministic type of quadrature. A deterministic type of quadrature that exploits the regularity of the function you're integrating, and it's a little bit more resilient to high dimensions than the brute force tensor type of discretizations or quadratures that I used before. Okay? So that's the idea. Okay. So what do you need now? Well, you need to introduce deterministic quadrature in the stochastic direction. So instead of using Monte Carlo, you use an interpolatory type of quadrature in the stochastic direction. So what you do, you have a function, right, in a given domain, 1D. You need to integrate it. First you interpolate it, and now you integrate exactly the interpolant. That's what you do. Now, as you raise the order of approximation of your interpolant, the quadrature becomes better and better and better. Okay? That's what we do. So we have a sequence of interpolants, right? And we're going to integrate them, and this is the rule. We have levels according to each of the directions of integration, and from the level you go to the number of points. So the level here to the number of points is because of the following. You have level 1, maybe you're using 3 points. In level 2, maybe you're using this many, and so forth, right? So sometimes you increase by 1 the number of points. Maybe you're using a Gaussian quadrature. Maybe you're duplicating the number of points from one level to the next. This is what this M of beta function encodes, right? It gives you the freedom to choose the relation between the levels and the number of points in the quadrature. Okay, and along that you also create single level single directional differences, and you tensorize them. And in the deterministic discretization, you use the same thing as before. So now you have two parameters, two multi-indices, beta and alpha. You put them together, and you take the whole mixed difference. Okay, so you compose the deterministic difference with the stochastic difference, and you just write the multi-index stochastic collocation approximation, which is just a sum over, again, appropriately chosen calligraph I set of these mixed differences. Observe now that this is a deterministic quantity. It's not a stochastic quantity anymore. Before, we were just working with alpha, and whenever we had to take an expectation of this, essentially we're taking a sample average with m alpha samples. Instead of doing that, we are just taking this delta S difference. So now, even though, again, this is deceivingly the same as before, it is not the same, because before we were thresholding with respect to the spatial discretization. We are thresholding now with respect to both the stochastic and the deterministic directions. Okay, so this I calligraph now lives in a higher dimensional space. Yeah? How do we choose this I set? Profits, again. This is the same thing. But for the same problem, this I set, we have a different shape. I mean, it is a different animal, right? Lives in another dimension, it's different. So this is the knapsack problem that I told you before. This is the profit, quasi-optimal sets. You threshold them as before, right? But now you're working in the alpha, comma, beta sets. And now we go to the assumptions. And I wrote here particular assumptions because, again, each problem will have its own assumptions. And I need to just to show you something, exemplify. So what am I exemplifying on? Is, again, the linear PDE that I was showing you before. Essentially, divergence of a coefficient times gradient of u equals f. Linear PDE with no time dependence. And in that case, you may have, as I am assuming here, analytic dependence of this y, right, of this solution with respect to this input y. Analytic dependence, means the following. Analytic functions are very well approximated by polynomials. How well approximated? Well, in the right regime, they are exponentially approximated with respect to the degree of the polynomial. Okay, and that is what is coming here. Essentially, in terms of the number of points that you use in the quadrature, the error is exponentially convergent. Again, you should. When I say error here, you should be careful. This is just the size of the mixed difference. So it's really a difference between approximate solutions. It's not really an error, right? In that respect, it's a contribution to the total sum, but it's not an error. And okay, so and this is the usual assumption of fixed order of convergence with respect to the finite element, and this is a blow up on the work with respect to the mesh size in the finite element, and this is just related to the work in terms of the number of points. I think here I should have written m of beta j and not 2 to the beta j. This is a misprint because we are using a general m here. Okay, but first observation, it doesn't look symmetric really in the work with respect to this term and with respect to this term. Okay. So it's this exponential convergence, stochastic variables, and algebraic. Okay, so let's see. Well, comments on this thing. These assumptions are fulfilled for this equation that I told you. Now the set. If you were just wondering what was the shape of the set, before in multi-index Monte Carlo, we didn't have this term. This term was not there, and we essentially have a linear constraint on the alphas, right? This new term coming out from the stochastic integration looks different, right? It will tilt in the alpha beta plane. It will tilt the set and will not make it linear anymore. So even though you're using the same finite element, right? The fact that you have changed in the integration rule in the stochastic direction makes it different. And you can show a result now on error estimates with respect to work, where this gamma now, at least if you work in finite dimensions, is not linked to, constrained below by 1/2. It is just related to the convergence rate of the finite element. Okay? So the finite element is the one that is constraining the convergence now, not the stochastic direction anymore. Now the rate is independent of the input number of random variables, but the constant is not. Okay, so if you just assume, like in this proof, that you have an isotropic problem, this constant will blow up. So if you go to infinite dimensions, you need to assume that somehow the importance of the different directions starts diminishing as n goes to infinity, which is a reasonable assumption, for example, in the light of these Fourier expansions that I made at the beginning as an example to show an example of how you approximate a field, an input field. Okay? This is a numerical test where we not only use the multi-index stochastic collocation, we also show the multi-index Monte Carlo and other methods as well. So this is a case that I showed you before in 3 dimensions where multi-level Monte Carlo actually doesn't do fantastic. So what you see here again is 10 random variables as inputs, dimension 10, multi-index Monte Carlo converging at the rate w to the minus 0.5, which is optimal. So it's behaving optimally, but compared to this method, it's just a dog, right? And in here, up to a log factor, essentially you can get w to the minus 2 as a convergence rate for the multi-index stochastic collocation. which is much better, right? I mean, it's a factor 4 between the two exponents. And multi-index Monte Carlo was behaving optimally. So it's a big deal. Is it clear now? I mean, this that looks so bad here is what I showed you before that was great. This shouldn't go unnoticed, actually. Okay, so this is much better. But again, it comes with assumptions. You don't fulfill the assumptions, you will not get this. Okay, so don't think that this happens all the time. You have to be careful when to use it. Now, you say, okay, maybe you have 10 random variables. Maybe that's boring. What happens if you have infinitely many random variables? Do you get the same stuff or not? So, when you give talks about these things, people say, okay, but how many random variables did you use? And I say the following: it's not really a relevant question, because you can have potentially an input with 1,000 random variables, but maybe 990 of them are irrelevant, because you just chose the problem in such a way that they become irrelevant. And actually, effectively, you were solving a problem in 10 dimensions. So you have to be careful, really, when asking this question. And what I say is the following, that instead of looking at how many random variables you use, essentially you should look at the class of regularity of the problems you solve. So suppose that actually the input is always infinite, right? But what matters here, if these are random variables, right, and they are bounded, for example, what matters is how these functions that are in front of them decay as j goes to infinity. If you have a slowly decay in series, right, this will be a hard problem to solve. If you have a fast convergence, right, and the psi j's becomes essentially zero after j equals 3, this will be a simpler problem to solve, right? Okay, so let's go a little bit into it. So now you define this kappa. Kappa is the log of the A is acting here, and kappa is defined by this size. The computation is trying to get the expected value of g. G is q of u, right? And we are just trying to use Curtis. And this is where it becomes a little bit technical. So essentially you say that you're going to consider s derivatives of these coefficients psi, right? And you will look at how fast the series of the norms of the psi j's measured in CS norm converge as j goes to infinity. Now you're going to put this summability PS here, and the problem essentially will become better as S becomes larger and PS becomes smaller. So the smaller the PS, and you still get something finite here, the better these psi j's are. Correct? Right? Is that clear? If I have a convergence series, right, of say a sub n's, and I take square root of these psi n's, well, the psi n's were the a n's were converging to 0, so the square root is a larger value. It will be more difficult for this series to become summable. If you take the 4th root, it would be even more difficult. If you take the 8th root, even more difficult. So somehow, the smaller the PS, and you still get something bounded, the better, the faster conversion were these psi's, right? This is what it means. So small PS, good problem. Large PS, bad problem. Large S here, good problem, because I can take many derivatives and can still get something bounded, okay? So large S, small PS, good problems, and vice versa, okay? Okay, so if you are in this context, then you can actually link these assumptions to the rates in these product rates. And you can have a theorem now that works in infinite dimensions, where you identify the convergence rate of the method now in terms of the work. This is bad because it means work of MISC corresponding to this optimal set. And now this R MISC is really what matters. So it says the following, that if the P is sufficiently, if this S is sufficiently large with respect to the work somehow, then you have this rate, and in the other case you have this other rate. You have, in general, like in this case, this really ugly convergence, because technically this is what happens. to get the best rate in space, you need to take derivatives of your coefficient. What do I mean? That if you're working with piecewise linear finite elements, you need to make sure that the solution is in H2 to get the best rate. But for the solution to be in H2, you need the coefficient in this PDE to be first order differentiable. So essentially, you're working with S equals 1. So this deteriorates a little bit more a little bit the rate of convergence of this series. For the best convergence in the stochastic direction, you don't want to take any derivatives. You want this size to converge as fast as possible. Think of this size as sine of jx. Whenever you take a derivative, a j pops up. Okay, so it gets worse and worse and worse. So you don't want to take derivatives, but to get the best rate in space, you want to take derivatives. The fight of these two is actually what makes this strange rate appear, because it's an interpolation type of estimate. But okay, this works in infinite dimensions, and you can actually work out you can work out in numerical examples. So this doesn't look as pretty as before, but I explain you. Each of these stars actually correspond to plot of convergences like this. So this is Multi-Index Monte Carlo, and this is the rate we are declaring, essentially. So we compute with our method here, and we check what is the rate, and then we put it in the previous plot. This is for dimension 1 problem with nu equals 2.5, and then dimension d equals 3 in this case, and nu equals 4.5. Nu is a regularity parameter. As nu becomes larger, the solution becomes better. So essentially, the kappa that we were talking about is a sum of cosinuses and sinuses, essentially. There's values here that are bounded, and these AKs are the ones that actually provide the regularity. They converge to 0 as k goes to infinity. And this nu actually make them converge faster. This nu is a positive parameter. And as nu becomes better, the problem becomes better. All right? So this is what you see here, that if you're working in 1D, as you start increasing the nu, you get to the rate of 2, which is the rate of solving deterministic PDE in 1D with this finite element that was linear, continuous piecewise linear. But if you are in 3D here, in the ranges of tolerances that work, you get more or less asymptotical to the rate 1.4. And you may wonder, okay, why not 2 and 1.4? It's just because there's a logarithm term. So I'll show you here. If you work in 3D with a deterministic PDE, essentially in the ranges of the work that we work, essentially, you get this rate, and this rate, if you fit just with the algebraic, is minus 1.4. But this minus 1.4 is actually indistinguishable from w to the minus 2 times log square. So asymptotically, this log square shouldn't matter. But because we are not working with, really asymptotical terms, we cannot distinguish minus 1.4 from w minus 2 to log w square. So it has nothing to do with the stochastic contribution. It's just a pre-asymptotical regime. Okay? So this is what you see here. Okay? There's also a comment to make in passing that this method actually works in high dimensions because they do not excite too many random variables at the same time. Okay, so the approximation in this multi-index stochastic collocation is like a sum of terms, and each of these terms activate a certain number of random variables. The number of random variables active in each of these terms seldom goes above 10. But if you look at the sum and you look how many active random variables you had, maybe it was 1,000 or 6,000. So it looks very scary when you look at how many random variables were really involved. But when you look at each of the terms, there were not so many. And this is why these deterministic methods become competitive. If many are active at the same time, there's nothing you can do. You should have to go to Monte Carlo. Okay. I think I came to the end. I can't believe it. Okay, so if you have questions, I think this is a good point to take them. Thank you.